Ready to learn ROS 2 and take your robotics skills to the next level? In this ROS course, I will cover beginner to advanced topics. Not only will I cover the important ROS 2 concepts, but I will also show you step by step how to implement the code. We will start off with beginner ROS topics such as how to install ROS 2, executables, topics, services, parameters, and action, workspace, Colcon build, creating your own packages, publisher and subscribers, and finally creating your own launch file. Later, we'll go into more advanced topics such as URDF for robot description, Rviz simulation, Gazebo robot simulation, ROS 2 control, camera, Lidar, and depth camera sensors in Gazebo simulation, talk about the SLAM toolbox, and end it with some robot navigation. So by the end of this ROS 2 course, you should have a solid understanding of ROS 2 concepts and be ready for real-world robotics problems. All right, let's get started. If you're new to my channel, I have a website at kevinwoodrobotics.com where I have a bunch of resources on robotics and computer vision. So check it out and subscribe to learn more. So first, I'd like to show you how to set up WSL so that you can use Linux on your Windows PC. This step is optional. It's for people that don't have a Linux machine or want to run Linux on your Windows PC. If you already have a Linux PC set up, you could go ahead and jump to the next section. So most of the steps I got will be based off of this website, but I just simplified it to the main key steps that I need to use to install it. First off, we go to the website, right? I use that for reference, but you don't need to. Just follow these steps here. So you want to open up a PowerShell. So you want to run as admin. So after you run as admin, you're going to open up this window here. So what you want to do is run the WSL install, and then after you do that, restart your PC and then come back to these steps. Then to see what distributions you have, you run WSL-list, and online, you're going to see these are all the distributions. So we will be using this one right here, 22.04. So after you run the install and your distro, you're going to set up your username and password. And if you do WSL-L-V, you should be able to see your Ubuntu here, okay? So that's how you do the setup for WSL. And then next up, you want to install your extension. So if you type in WSL, go ahead and install your extension here. And then you want to open up WSL in VS Code like I have here. What you want to do is run Ubuntu and then just type code dot. So if you do code dot, you'll see this window here pop up. Then you should get up and running like I do. So before we can do anything in ROS, we need to make sure we have ROS installed. So the specific version that we're going with today is the Humble version. The reason I chose Humble is because the release date was from 2022, so it's been around for a while to be pretty robust. And the EOL date, the end of life date, is in May 2027. So we still have about 2 years left, so that's pretty good. You can see that the next best one, if you're looking for an alternative, would be Jazzy, which has an end-of-life date of May 2029. So without further ado, let's jump right into the installation process. So you want to first run these commands to set up your locale. We're using a UTF-8. And then after that, you want to do some software properties and universe repo install. Then you want to set up your curl install and your ROS key setup here. Then after you do that, you want to source your configuration. Then do an update and upgrade. Then what I'm doing here, this is the main installation step, is doing the full desktop install. So just run that. And then the next step is what you want to do here is if you run this, you want to source it. So this will allow the ROS2 command to work. So when you hit ROS2, you should see something pop up here showing that your ROS2 has been installed properly. So in order for you to use ROS2 commands, you have to do what's called sourcing your ROS2. So The point of sourcing is so that you let your computer know where the ROS2 installation is located, and that way you can use the ROS2 commands. If you don't do this step, you're going to have to either manually source ROS2 every time, or you could do what I'm about to show you, which is setting it up in some of your configuration file. So you're going to see this thing that says ROS2 command not found. So you typically will see this if you forgot to source your setup.bash file. So the best way around this is to set it up automatically. So you could put it in your bash src file. So this will allow your ROS2 command to work every time. You could run it the command way by running this. Or for me, if you're in VS Code and you like to do things the GUI way, what you can do is go to your bash src here, and you could just add in this step, opt ROS humble setup.bash, so that every time you open a new terminal, it will set up everything for you. So when you want to run a program in ROS, you typically run what's called an executable. So you could think of an executable as the program that you're running. And these programs have been typically built by some source code using Colcon, which are some tools we'll talk about later. But for now, just treat executables as programs in ROS. And they're located in what's called packages. So packages are something that holds a bunch of code and other instructions on how to build it or any other configuration files. But for now, what you need to know is that executables belong in certain packages. And to run a program, you would run the executable. So I'm going to show you step by step how to actually use the commands right now. So first off, we're going to use the turtle sim. So you want to run these two steps to update and install the turtle sim package. So after you do that, you could list out your package by doing ROS2 package list. So you can see these are the lists of the packages available. So if we look here, we can see that our turtle sim package exists. And we can also see the list. We can see all the executables. So you can see ROS2 package executables. So here you can see that these are the things Turtle Sim offers. Okay, so that's for the executables. And we could do specifically just for the Turtle Sim package, we could do ROS2 package executables and just type in the package Turtle Sim. And you can hit tab to complete these things. So you can see for Turtle Sim, there's only 4, so this isolates the list that we're looking at. Okay, so where is this Turtle Sim package? So what we could do is check out, here goes cd opt, and then we have ROS humble, and we hit enter, hit ls. You can see that it's actually going to be somewhere inside here, but let's open up a new terminal here. So here I open up the terminal, and if I hit Control P and I type in turtle sim, you're gonna see that it's in here. Okay, so this is the executable. It's gonna be in share ament index. You can see it's in this path here. So if I scroll up, you're gonna see ament index, resource index, packages. So that's where you can locate it, and it's all under the share folder here. Okay, so that's what you could do if you want to find where some of the packages are located. Okay, so after you do that, maybe we want to run the package. So if we use the run command, it's going to have the package name followed by the executable name. So I'm going to do ROS2 run, and you can always do ROS2-H to see the help. Okay, so you could ROS2 run, and then the package name was turtle sim. Hit tab to complete, and then we're going to do the turtle sim node. So if we run this, we should see the turtle sim node running. Okay, so this is our turtle right here. And then the next up, we could use our teleop key. So I'm gonna slide this window over a little bit. I'm gonna close this. So just gonna rearrange a little bit, and you can see if I run another node called, let's see, I'm gonna say ROS2 run turtle sim. The next node is called turtle teleop. So this will allow me to move the turtle. So let me just slide this over a little bit more so you can see. But you can see if I use the arrow keys and the forward, you can see my turtle is moving. So the way ROS works is they communicate between what's called nodes. So these nodes are typically responsible for sending or receiving data. And you could do this through different ways like topics, services, or actions. I'm going to be going over the different types later on, but in this video, we'll be focusing on some of the commands you could do to use your nodes. You type ROS2 node-h, you'll see the help for the ROS2 node. And then we could do ROS2 node list. You could see it's one of the main function, ROS2 node list. You can see that if I run this, there's no nodes running right now, right? So let's go ahead and run a node first. So we do ROS2 run turtle sim node. So we have our turtle node up and running here. So we have, once you do that, and if we do ROS2 node list, we will see that turtle sim is a node that's running. Okay, so we could do different things to see the info. So if we do ROS2 node info and we type in the node, we could see different things about this node. So what this shows is there's subscribers, there's a publishers, there's a service servers, and then as well as the clients, action servers, and action clients. And those we will talk about later on in this video. But for now, you just know that by using a ROS2 node info command, we could find out more info about a certain node that we're dealing with. So previously we looked at nodes. Now we're going to dive deeper into topics. So topics is the thing that connects two nodes together. So you can see on the left we have a publisher node, and on the right we have a subscriber node. So the idea is a publisher node is going to send data to a topic, and the subscriber node is going to subscribe to that topic to receive that data. So in this video, we're going to be covering some of the commands you can use for ROS topics. So first off, let's start two of our nodes. So we'll have ROS2 run turtle sim and then turtle sim node. So this is our turtle sim node up and running. And then we'll go ahead and run another one. That's ROS2 run turtle sim and then turtle teleop. Okay, so this will allow us to control it. As you can see, we're moving our turtle. Now, what we can do is we could list out the topics. So we could do ROS2 topic list, and this will show all the topics. And then if we add a -t to this, we could see the type associated with the topic. Okay, so in this other window, we could go ahead and open the RQT graph. So you could see this is our node, and if we refresh, this is everything that's talking. So you can see between turtle sim and turtle teleop turtle, the command velocity is being passed through. Here's some action that we'll talk about later on, but for now we'll focus on this right here. So you can see our command velocity is one of the things listed. So if we want to see the specific topic output, we could have another terminal, and then we could say ROS2 topic, and then we could do echo and the topic name. So in this case is turtle1 and then the command velocity. So what this means is as I move the turtle, it's going to output the topic. Okay, so that's what this does. And we could view the info by using the ROS to topic info, and we could pass in the topic name, which is command velocity. So we could see that subscription count is 2, publisher count is 1, and the type is geometry messages message twist. So another way we could see the interface definition is we could run this ROS to interface show, and then we have our geometry messages, and then as we saw here, it's going to be the twist. So if I enter this, you're going to see what this takes in is a vector3 linear of x, y, z, all floats, and the angular part is also float 64 for the x, y, z. Okay, and we can also try publishing the data at a specific rate. So it's going to follow the ROS. It's going to have the form of ROS to topic pub, and then the once just means that it's going to do it once and then exit. And we're going to pass in the topic name, the message type, and the argument, which here is going to be the command. So if I copy this and I run this, okay, so ROS2, you can see it just drew. And if I do it again, you can see it drew again. Okay, so that's what this does. And notice that if we look at the whole command again, we have the ROS2 topic pub once, the topic name, and then the type, and then the message. So we saw that it's going to be XYZ for the linear, and then XYZ for the angular. Okay, and we can also publish the data at a specific rate. So this right here is ROS2 topic pub with rates at 1 hertz. And then again, we have the topic name, the type, and then the message or the goal. Okay, so if I run this, you can see it's gonna just keep going in a circle because it's at a certain frequency. Okay, so I'm gonna go ahead and stop this. Now what we could do is ROS2 echo, and we could see the pose here. So actually, let me just run this again. So here, let's just go ahead and open up another one. So here I'm gonna have ROS2 topic echo, and then the turtle pose. You can see that it's outputting the pose as this turtle is moving. Okay, and if we come back here and refresh this, you see that we added the pose here, okay, because now it's outputting. And we can also view the topic frequency here. So I'm going to go ahead and stop this. If I do ROS2 topic hertz and the topic name turtle1 pose, well, now the pose, you can see that it shows us the average rate, min, max, standard deviation, and the window. Okay, so this will tell us the frequency. So previously we were looking at how publisher and subscribers would communicate between topics. With topics, what we notice is that there's a stream of data that's always continuously being published or subscribed. With services, it's a little bit different. There's no concept of continuously publishing. Instead, what happens is you have a server and client relationship where a client is going to request some data, and then the server needs to respond before the client can receive the data. So let's go ahead and take a look at some of the commands for services. So let's go ahead and start off by running 2 of our nodes. So ROS2 run turtle sim and then turtle sim node. And then in our another one, we're going to run our teleop. So we're going to have ROS2 run turtle sim turtle teleop key. Okay, so as you can see, our turtle is moving. So here we're gonna do we're gonna list out their services. So we do ROS2 service list. You can see these are all the services. So under the turtle one, we have all of this stuff, and then all under teleop turtle, we have all of these things as well. So we could see the type associated with it by adding a -t. So this gives us more details if we need to use that information later on. So we can also find the service with a specific type. So we could do ROS2 find, and then you could pass in the type. So for example, if I want to do this one here, std, and then sr, let me just copy that. So you can see ROS2 service find, it'll tell us that clear and reset will have this type here. So you can see if I look through this, let me just drag this a little bit, but you can see that clear has this type, reset has this type, as we expected based off of the output. Okay, and we can also see the interface, so we could do ROS2 interface show, and then the service type. So we could do turtle sim srv, and then let's say spawn. So you can see for spawn, this is the output. You have a float x, y, and theta. And then you have the string name, which is optional. Okay, so now that we know how to the details of that, we could look at calling it. So for calling it, let's go to a new window, and if we do ROS to service call, and then let's say we want to clear, and then we need to pass in the type, so std service empty. You can see that it cleared the drawing that we had here. Okay, and then now if we want to spawn a new turtle, we could do ROS to service call and then spawn, and we'll have our turtle. You can see that here, let's actually change the location. So, or if we drag this, you should see it. You can see our turtle got spawned over there. Okay, or let's just choose this location so you can see it more easily. You can see our turtle got spawned over here. Okay, so for that one, you can see the function argument is service call, and then your service type, and then here is the format of the specifications for what you wanted based off of this interface. Okay, now let's talk about parameters. Sometimes when you want to input data into a node, it's convenient to pass parameters into your node, especially if you have different configurations for different type of robots you're working with. This is very good to have different inputs to your nodes. It's kind of like having inputs to a function, but in this case, our function is a node. So let's see some of the commands we can do to work with parameters in ROS. So let's start off by running two nodes. So we're going to do ROS to run the turtle sim and then turtle sim node. And then in our other one, we're going to run the teleop. So let me move this to the side. So we're going to say ROS to run turtle sim and then turtle teleop key. So you can see our turtle is moving. And then next up, we're going to list out our parameters using ROS to param list. So this is the list of our parameters, and you can see the turtle sim one, we have these parameters. So we'll play around with the background a little bit. So we can actually get the parameter value. So to get that, we could do ROS to param get, pass in the node name, which is turtle sim, and then the parameter, so background, and then background G. So you can see it returns 86. We can also do something similar, but this time as you set, you pass in an extra argument, which is a value. So do ROS to param set, pass in the node name, and then the parameter background G, and we'll pass in the value of 255. And you can see the background has now changed. Okay, so you can also view all parameters for a node by using the dump function. So you could do ROS to param dump, and then pass in the node name, turtle sim, and you can see these are all the current values that are set for the backgrounds. You can also store all of these inside a YAML file, so you could do ROS to param dump, and we'll pass in the node name, and then our file is going to be turtle sim.yaml. So all of our parameters will go inside this YAML file. And if we look inside here, we can see these are all of our parameters that we have stored. Okay, so the beauty of this is you could load in your param file. So you could do ROS to param load, and then pass in the node name, and then the file, which is your turtle sim.yaml. And this will load in to whatever setting you had. But since we're already blue, you didn't see a change. But another thing you could do is load the param on startup. So you could actually do ROS to run, and you're going to pass in the package name, and then the executable name, which is turtle node, and then all these additional arguments here. So you have after turtle sim node, you're going to see turtle sim node, and then -- ROS args, and you're going to do params file -- params file, and then turtle sim.yaml. So this should open up a new window with the light blue background. So now we're going to look at ROS Actions. This ROS Actions uses the same server and client model, but with a twist. So the thing that we're adding to it is it's going to have a goal, feedback, and results. So we're going to be looking at the different commands in ROS that we can use with actions. First, let's run 2 nodes. So ROS to run turtle sim node. And then in the other one, we're going to run our teleop. So let me slide this over. So we have ROS to run turtle sim, turtle teleop key. So you can see our turtle is moving. And then in the teleop window, what we're going to do is observe the following. So if we press G, you can see that it's rotating. And you can see here it's going to tell us the status. So if we press one of the letters and cancel early, we're going to see something else happen. So if I press F here, it says rotation got canceled, right? So I do it again. Pretty much anytime you press a key and then you press F, it's going to say goal canceled. And then if I try toggling between 2 commands here, you're going to see that rotation goal received before a previous goal finish, aborting previous goal. So it's always going to take the latest goal command. So that's one of the beauties of actions. So we want to see the action clients in node info on the bottom. So if we do ROS to node info, and we're going to pass in teleop turtle. So we could see all the info for this node here. And you could see specifically in the actions, there is this absolute, the rotate absolutes that we've been monitoring. Okay. And we could do a ROS to action list. This will show all the actions, and you could see -T for the type associated with it. Okay, and we can also see the action info. We could do ROS to action info and then pass in the action name. So we have turtle1 rotate absolute. So this will tell us the action clients, action servers. So you can see the client is the teleop and the server is the turtle sim. So we can see the data type for the action by using the interface. So we do ROS to interface show and then pass in turtle sim action rotate absolute. We could see that it communicates by using float 32 of theta. Okay, and then that's desired, and you have the angular displacement in radians. It's also it's going to be a delta. Okay. So we could go ahead and now send action goals following this structure called ROS to action send goal. And then you pass in the action name, action type, and the goal. Okay, so if I copy this line here and if I run this here, you see I have ROS to action send goal, the turtle1 rotate absolute, and the turtle sim action rotate absolute. Okay, so if I go ahead and run this, you're going to see that it moved. Or actually it was already somewhere else. So if I make it go elsewhere, like D, for example, and then I run this again, you're going to see it rotate facing up. So up until now, we have just been using ROS code that was provided by ROS. We haven't really created any of our own packages yet, but now we are going to start doing that. But before you can do that, you have to understand a concept in ROS, which is called the ROS Workspace. So the idea of the ROS Workspace is pretty simple. It's a way that you organize your folder structure so that you can place your packages in your source folder. So the typical process will look like this. You're going to have a folder, which is your workspace. So you can think of folder and workspace as the same thing. You want to give it a name that's representative of your workspace. In this case, because it's a demo, we're calling it ROS2 Workspace. You can have more than one workspace at the same level if you wanted to. But the main idea is that the ROS2 Workspace is going to hold the different files that we want to build and run that contains our source file and install files. So the main part that contains our packages is going to be under the source folder. So this source folder is going to be a folder that you need to create after you've created your workspace folder. So you create ROS2 Workspace folder, and inside you create the source folder. Once you do that, you're going to set up a package, which we're going to go over in a later video. But the main idea is that when you create a workspace, after you create the source folder and you do some building with Colcon, which we'll talk about, the folders here, the build, install, and log folders, these folders here are going to be generated. And inside of these folders are going to contain executables and other information that allow you to run your executable. So now we're going to talk about the Colcon build tool. So Colcon is a command line tool that you can use to build your packages. So previously we've been using only code that was already pre-made. But now we may want to make changes to the code or even write our own code and build our executable files from our source files. So that's where Colcon comes in. And just as a reminder, we have what's called packages. So the packages will typically be inside the source folder that's under your workspace. So here is the Gazebo tutorial. This is a name of a package. I'll be covering Gazebo later on, but you'll see that inside of the Gazebo tutorial package, you're going to have more folders. So you may have a config folder, include folder, a launch folder, a meshes folder. But the main part that all packages have is it's going to have a source folder, which is going to be your source code. And you're going to have the cmakelist.txt, which is going to help with some of the build process. And you have the package.xml, which will support the build process as well. Okay, so now let's go ahead and take a look at some of the commands we can use with Colcon to build our packages. So first off, you want to run this command here to install your Colcon. I've already done that. And then you could make your workspace and navigate to your workspace. So go ahead and do that. I already made my workspace, so I will just navigate to my workspace. And then what you want to do is you want to add some source code to your folder. So you're going to git clone from here some ROS tutorials. So I've already done this step, but just do that. And then what you want to do next is set up the Colcon tab completion. So you could do echo and then insert this autocomplete command here, and then this will get your Colcon tab completion up and running. So here we're going to do the build step. So what we're going to do is run Colcon build symlink install. So here it allows us to install, and the symlink, what that does is it's going to prevent copying the files and just make a symlink to your files. Okay, so let's go ahead and build our package. So we do Colcon build and then --sim. Okay, so I just hit tab and the autocomplete is working. So this will go ahead and build it. Okay, so the build took 21 seconds, and then after it's done building, what we want to do is do ls, and we could see the contents of this folder. So you could see that we have a build, install, and log folder. The next step is to source your folder. So we want to run this command, source install local setup.bash, and this will allow us to run some of the packages that we just built. So here we do ROS2 run turtle sim and then turtle sim node. So this will be our turtle sim node up and running. And you may think that this might be the same one as the original turtle sim. So let's do some modifications so you can see that it's actually different. Okay, so let's go ahead and find our file that has the name of our turtle sim. So inside our turtle frame, you could hit Control P and search for the turtle frame file. And then after you do that, you could come in here and we could just add in my name, Kevin. So what this will do is if we go back to our read. Okay, so here we edited that, and then we just want to redo our build step. So I'm just going to go ahead and copy this again. So I'm going to rebuild it and then source it. And after it's done building, we could go ahead and run our turtle sim node again. So now that I have this up and running, you notice that the name has changed to Kevin. So that proves that we are editing our local turtle sim. So we just saw how to build packages with Colcon. Now we're going to talk about how to create your own package. So this is good if you have your own custom code that you want to run in ROS. And that's when you will want to create your own package and build it using the steps we just described earlier. So now let's go ahead and take a look at the commands that you need to use to create your own package in ROS. So the prereq is you want to install Colcon and create your workspace, which we did in our previous video. So do that if you haven't done that already. And then to create our package, what we're going to do is navigate to our source. So cd source. So we're in ROS2 workspace source. And then you want to run the create package command here. So this command is ROS2 package create dash dash build type amend cmake, and then the node name, the name of your node, and then the name of your package. So if I go ahead and run this, it's going to create my package. And we could go ahead and check out the folder that it made. So if I go to source, my package, you see that inside my source, it created my node.cpp. So if you look here, this is just my CPP file that says hello world essentially. So you could see this. And then you have my CMake list. These are all the build instructions. And then the package.xml is all the meta information like your email version and whatnot. So that's the essential basics of your package. Okay, so here we're gonna go ahead and run. We just created our package and now we want to build it. So here we want to cd ROS Workspace, and then now we're gonna do Colcon build dash dash package packages select, and then do my package. So this will build our package. So this is a short package, so it's gonna be pretty fast. And then now we're gonna do source install our local.setup.bash. And then I could go ahead and do ROS to run my package and then my node. So you can see it says hello world. Okay, so that's the program running, and we got everything up and running. So that's good. So in an earlier part of this video, we discussed how to use publisher and subscribers. Now we're interested in creating and building our own publisher and subscriber package using Colcon. In this specific part of the video, we're going to be showing a C++ version. The one right after this will be a Python version. So let's go ahead and see how to create it in VS Code. But first off, we're going to be using CMake in here. So if you're using VS Code, you want to install this CMake extension. And first off, if we want to create the package, we want to run the command to create the package. So you want to go to your source folder in your workspace and then run this command here, ROS2 package create build type amend cmake cpp pubsub. That's going to be the name of my package. So I hit enter, that will create my package. And then you can see here it creates a folder. And this is a folder that's my package, which has to include the source, the CMake, and the package .xml file. Okay, so we're going to take a look at the source code that we'll be using for this tutorial today. So there's going to be two main functions that we're playing with. So the first one is this right here. This is the publisher function. It's going to be the publisher member function.cpp, so you could get it in my repo. But these here are the includes that you need to include. So this is for the timing and the memory stuff, strings. This is the ROS related things. So this is the basic includes that you need for a typical publisher function. And here we have some resources on C++ classes and inheritance if you need some refresher. But here what we're doing is we're inheriting the node class to make our minimal publisher class. And then inside of here of our constructor, we're initializing these values here. And we're going to be creating a publisher here. And this publisher is actually a shared pointer. So I have some videos on shared pointers as well. You could go check that out. It's going to be under the smart pointers. But you could see here in the private, we have defined these smart pointers here, shared pointer specifically for the timer and publisher. So when we create this publisher, we're saving it to this publisher shared pointer. And similarly here, we create a wall timer and we're storing it in the timer shared pointer. So this right here is going to be doing a callback. You pass in the callback function. So our callback function here is the timer callback. And what this will do is it's going to spit out the message hello world. and then publishing the message here that it's going to be updating. And you see it's based on this data.c string. But here, the hello world here, it has a count plus plus. So we have a variable here that we have, and we're just incrementing at every iteration. Okay, so that's what this does. And then here is the main loop. A lot of these functions will follow a similar structure. So here we'll do some initialization and then the spin. So this will create an instance of the minimal publisher and enter loop, and it keeps a node alive with the callbacks up and running. And then after you're done, we do a shutdown, and that's the gist of it. Here is the subscriber member function.cpp. So this one, once you publish, someone has to subscribe to it. So here again, we do inheritance, and then we have our constructor to create our minimal subscriber. And inside the subscriber, we create a subscription. This right here is a shared pointer, as you can see. And this will do a topic, and then this will have our callback. So in our callback, all it does is respond to what it's getting back. So it'll say, I heard message.data, and whatever the message is, you will get that response back. And in the main function, we have a init, spin, and shutdown, which is similar to our publisher structure that we just talked about. Okay, so what we want to do is get those two functions. We want to extract those two functions, and we want to put it in our source folder. So again, these are some resources. You guys could check it out. But what I'm going to do is just copy those two files that we just went over, and then go right into here to our source file in our cpp pub sub in our source. We're going to paste that in there. So those two functions are in there now. And then the next step is we want to update our package.xml and our cmake list.txt files. So if we take a look at that, we see this is our cmake file here. So what we see is that the cmake file, the general structure is it's going to make the project, have some cmake minimum requirement, and then the part that we're actually adding is this chunk of code right here. So when you create a cmake list by default, when it's created during the package generation, it's going to look something like this. And then the cmake list that we're going over is what we're adding onto it. So the things that we're adding onto it is we're going to add some lines to find our packages that we're using. And then for the publisher, what we want to do is add an executable. So it's going to be called the talker, and then it's going to tie it to our publisher member function.cpp. And then this will do the dependency linking for the talker and the things that it'll use. Similarly, for the subscriber, we'll do the similar structure. And then the installs here will set up our targets for running. And then this right here is for some copyright and licensing that we won't really care about. And then this is the final step to make the package. And then for the package.xml, the part that we're adding to the originally generated file is this part here, the depend on the RCL CPP and the STD messages. Okay, so I'm going to go ahead and copy those two files, and I'm just going to delete these two, and we're going to update with our new file here. So if I paste it, these are our updated files that we'll be using. So if we go back to our README, what we're going to do, now that we have updated our files, you could run this step here to check for missing dependencies. This one I would say is optional, but you want to first go back a folder and then run this. So this will do any dependency check. So the final step is you want to build it using Colcon. So we're going to run the Colcon build package select, and then the name of the package is cpp pubsub. So if I go ahead and run this, this will build my package, and it'll take a few seconds to build. But once it's done building, we could start using the package. Okay, so when we do, after it's done building, we would create another terminal, and then we would cd to ROS to WS. The more important step is to source it so that we could find the talker file, and then we could run ROS to run cpp pubsub talker. So if I go ahead and run these commands, what this will do is start publishing. And then in my other terminal, I could use the listener. So here in my bottom terminal, I could cd source and then run the listener, and you can see that it's getting the feedback of what it's hearing. Okay, so now we're going to see how we can create our own publisher and subscriber ROS package in Python this time. It's going to be pretty similar, but there's going to be a few differences, so pay attention to the differences if you're trying to implement this in Python. We're going to create a package from our ROS2 workspace source folder, so we want to cd into that, and then run the ROS2 package create command to create our package called pypubsub. So if I go ahead and run this, it's going to create my package, and you can see in my folder here, we have a folder called pypubsub, and by default, it's going to have a pypubsub folder with a init.py function here, and then a resource folder, a test folder, a package.xml, a setup.cfg, and then a setup.py. Okay, so we're going to look into some of the source files that we'll need. So we have a publisher member function here, and this is what we'll do the publishing. So I have some resources if you need some refresher on Python classes and inheritance here. But here what we have is we have a minimal publisher that inherits from a node, and we have a constructor here. So here in the constructor, we initialize with the name of the publisher called minimal publisher. And then we have a self.publisher variable that we're storing as a member variable after we create the publisher with our string, the topic, and 10. So we pass that in, save it, and then we have a time period of 0.5. And then the timer, we're going to create a timer and then store that timer. And then we have a counter variable I that starts at 0. And we have our callback function here that's going to get our message as a string. Data is going to be hello world, and then it's going to spit out the number that we're retrieving. And then here we have the self.publisher. Publish is going to be publishing the message. And then here is going to be what is going to output what is publishing. And inside of our main function, we have the similar structure as we mentioned in our C++ video. But here we have a init, and then we instantiate the minimal publisher, and then spin will get it up and running. And then when you're done, it'll do some destroy and shutdown. Okay, so here's a subscriber. We have the subscriber function here, or the subscriber file. So here what we see is a minimal subscriber. We're going to inherit the node. Again, we create a constructor with the name of our subscriber. And then we're going to create a subscription with string, topic, and then a callback. So here our callback is going to be I heard some message. And then inside of our main function, we're going to call the init, call our minimal subscriber function or class. We're going to create an instance of it, and then spin, destroy, and then shut down. Okay, so that's the general structure of the publisher and subscriber functions. So next up is we want to update some of our files. Specifically, we have our package.xml and our setup.py. So let's take a look at what changes we made. So here is our package.xml file. As we see by default, it'll generate these files, but what we're going to do is add these two lines here, the rcl.py and then the std messages, so that we can use some of the ROS functionalities. And then in the setup file, what we're going to do is add these two files here, so or these two lines here. So inside the entry point, we have a talker. So this will set up our pypubsub, and then our publisher member function, and then our subscriber member function. And this will allow us to use those functions that we created. So back to my README, let's go ahead and make those updates. So we saw the things that we have. Now we want to move it over. So we're going to copy these two files here, which is our source files. I'm going to copy it. We're going to our pypub folder here, and then we're going to paste it in here. So those are our functions. And then we have our package and setup.py. We're going to copy those. We're going to go ahead and just remove those two files since we're changing it. And then we'll go ahead and update that. So if we go back to here, we're going to paste it. We have our new updated package and setup files. So now that we have our updated files, what we're going to do is we're going to do the ROS. This right here is to check for missing dependencies, which I would say is optional. But you want to cd back to your previous folder and then run this so everything is up to date. And then we're going to build with Colcon from ROS2 Workspace. So I'm going to copy this. Colcon build package select pypubsub. this is going to build our package. And after the package is done building, what we want to do is create another terminal and then run the talker from our ROS2 workspace. So before you do that, you need to source it so that the talker command will show up. So if I go ahead and run this, this will start my talker. And then in the other terminal, we want to start our listener. So to start our listener, we're going to run the similar command, but now with the listener. So here we have our listener, and you can see that it says, I heard hello world and the number that it's publishing. So now I want to talk about launch files. So up until now, we have been writing our commands in the terminal when we want to execute something. So for example, if we're launching a publisher or subscriber, we would do it in the terminal and write the commands there. Sometimes if you have a lot of things you want to start for your program, it could be pretty tedious to write it line by line in different terminals. So that's where launch files come in. Launch file allows you to automate this in a Python script so that you can call the different commands just by writing it inside of your generate launch description function that you can see here. So each launch file is going to be different case by case. You may have a different one for different packages, and you could customize this based on the specific nodes that you want to run. So this is just an example of a launch file, which I'll be using later in this video. But here you can see that I'm running a launch file here. So you can have a launch file that calls a launch file. So this is what this is doing. You could create a robot description. Again, it's a topic we'll talk about later on. But here you can see that you could launch a robot state publisher node by using these commands here. So you would call node, set the package, executable name, and if there's any parameters, you could pass parameters inside of your node as well. So here you can see we have a joint state publisher node. So there's a bunch of nodes that you could set up here. You can also call the execute process. This allows you to run a ROS terminal command directly from your launch file. And after that, you're going to see all the way at the bottom, the final step is to return the launch description with all of the function calls that we just went over earlier. So to actually run the launch file, what you would do is run the command ROS2 launch followed by the package name and the launch file name. So in this specific case that we were looking at, it would be ROS2 launch Gazebo tutorial and gazebo.launch.py. So you're going to notice that the typical structure of launch file names is going to be something.launch.py. So just go ahead and follow that convention. Okay, so now I want to talk about URDF files. So when you have a robot, whether it's in simulation or in real life, you need a way to tell your program how this robot is described. So we do this by the URDF, and we're going to see some of the conventions and how to actually create one from scratch. So let's get started. I will go over what is an URDF file, the general structure, go through the general structure of a link, talk about the visual, types of geometries used in URDF files, the origin, RPY, and XYZ, material property, collision, inertial, a link example, talk about types of joints, parent and child link, origin and axis, dynamics, limits, a joint example, and finally, we'll go over a robot example. So by the end of this video, we will see how we could control R2-D2 in Rviz by using these sliders on the right. So what is an URDF file? So URDF stands for Unified Robotics Description Format, and it's a .xml file used to describe the visual, physics, and connections of a robot with joints and links. So here is a general structure of an URDF file. So we typically will have an XML version on the top. We'll have a robot name. And then it's going to be broken up into two sections typically. So you have a link and a joint. So inside of the link, we'll have a link name and have the visual, collision, and inertial properties. And inside of the joint, we're going to have axis, parent link, child link, origin, and so on. So this is the main structure that we typically will see. And if we take a look at a generic joint, it typically looks like this, where we have a joint which has a frame. And then each of these other components, like the visual, collision, and inertial, will have a frame as well. So now let's dive into the links in an URDF. So a link is used to describe a segment of a robot. So you could define a visual, collision, and inertial properties. And the geometry and origin properties are used in the visual and collision properties to describe the shape and location of the link. So you could take a look at the general structure of a link. So here we've expanded into our previous structure for the link. But when you describe a link, you could go into details for the different parts. Some parts are optional and some are required, depending on what you have. So you can see inside the visual, we have a geometry, which will have a geometry-specific code. And then we'll have an origin that's described by RPY and XYZ. And then we have a material that will have some color that we define. And inside of the collision is similar from the visual in that we will still have a geometry, and then we'll also have an origin. And then in inertial, we're going to have something new, which here is the mass in kilograms as well as the inertia. So the visual part of the link is used to describe the geometry of the link, and usually this can be an accurate representation of the robot or just a simplified version depending on the goal that you have. So for accurate models, you could probably use a 3D modeling software like SolidWorks, and you could export the STL file to get the geometry. So there's different types of geometries used in URDF files. So typically, you're going to see things like boxes, spheres, cylinder, and meshes. So for box, sphere, and cylinder, you define it using the geometry-specific code, as you can see here. So box, you use XYZ, sphere, you use a radius R, and the cylinder, you have a radius and a length. And then for meshes, you're going to have a file path to your STL or DAE file, and then you have a scale depending on how you want to scale your part. So the origin, which controls some of the frame locations as well as the orientation and position of your parts, defined by RPY and XYZ, can be quite confusing. So let's go ahead and take a look at what that is. So the origin is used to define the rotation using the roll, pitch, yaw, as well as the translation using the XYZ relative to the link's coordinate frame. So the order of rotation for RPY is ZYX. So first rotate about the X, and then about the Y, and then finally the Z. So the rotation operation is applied first, and then the translation. So for the visual and collision part, visual and collision, the origin describes how the geometry is transformed relative to the link's frame. So for inertial, the origin describes the location of the center of mass relative to the link's frame. So for the origin, typically is defined with the syntax RPY equals RPY, and then XYZ equals XYZ. And we will see the axis colors usually defined by red, green, and blue, which corresponds to X, Y, and Z. So for the material property, is used to define the color as well as the transparency of your color using the RBGA, and it's going to be normalized from 0 to 1. So the syntax for that is you have a material name equals color name, you have a color RBGA equals to RGBA. So some common colors you might see would be, for example, red would be 1001, green would be 0101, and blue is 0011, yellow is 1101, and then finally cyan is 0111. Now, if you want to define the collision property can be used to describe a bounding shape around the link for collision detection. So usually people use simplified shape for this for faster calculation when detecting for collision between other collision bounding shapes. So the syntax for that is you have a collision tag, and then inside of here you have a geometry, which you will have a geometry-specific code. And then to define the origin, you could set the RPY and XYZ. The inertial tag is used to describe the inertia and the mass of the link. So to do that, you have the general structure here, which you will have mass. This mass is in kilograms. And then the inertia, you have the IX, IXY, IXZ, the IYY, IYZ, and then IZZ. So let's go ahead and take a look at a simple link example. So this simple link example here, we have defined the material for blue, and then we have a link name called base link, and inside of here we define our visual. So inside of our visual, we have a geometry, which we're using a cylinder, and we have our origin. So our origin, we're not moving, and then we define our material here as blue. And our collision, we're also defining some geometry that's very similar to the actual visual part. And also the origin, we just keep it the same. And then here, for the inertial, we just set as some mass values and some inertia matrix. So let's go ahead and run this launch file, which will allow us to visualize our simple link URDF file. So you can see here, this is just a simple link, and you can see that everything is up and running, which we expect, which is a blue cylinder. So the general structure of a joint in a URDF file is it's going to have a parent link and a child link. So inside of here, we have an example of a joint. So we have a joint name that has the name of our joint, and then the type of joint, which we'll talk about later. And then here is the parent and child link, which we will have a name for it. And then we're going to have an origin, axis, and a limit. So then we're going to have a dynamics for it as well. So the limit is going to depend on the type of joint, which we'll talk about later. But after you have everything for this, you'll have a complete joint that can connect your links together. So the types of joints that you have, there's a different few ones that you can use. So you have a fixed, which will have no motion between links. You have a continuous, which will have a rotation about the axis, and there's no limits. You have a revolute, which is rotation about axis with limits in radians. You have a prismatic, which has the translation about an axis. You have a floating one, which will have 6 degrees of freedom, so 3 translation and 3 rotation. And finally, you have a planar, which will have a motion on a plane with 2 translations and 1 rotation. So the parent and child link here is you're going to have a parent link with the name of your parent and a child link with your name of your child. So this is usually like the order that you define your links. So you're going to have everything is going to be relative to something. So when you start expanding more links, you have to keep track of what comes first and what comes later. So for the origin and axis in terms of joints, the idea of that is a little bit different from links. So for joints, what we're actually doing is changing the frame location. So the origin describes the location of the child frame relative to the parent frame. And the axis describes the axis of rotation for the joint. So the syntax for that is RPY equals RPY and XYZ equals XYZ. For the dynamics will include the damping, which is expressed in newtons seconds per meter, and then the friction, which will be the static friction expressed in newtons. So the syntax for that will be damping equals the damping coefficient and friction equals the friction coefficient. So for the limits are for revolute and prismatic joints only. The lower and upper fields are in radians or meters, respectively. And then the effort is the max effort in Newton meters. And velocity, similarly, is going to be the max velocity, but in radians per second. And the syntax for that is going to be like this. So limit, lower, upper, effort, and velocity. Now let's go ahead and take a look at a joint example. So here we have a simple joint URDF. So let's go ahead and open that file. So here we have a simple joint. So inside of our simple joint, what we have defined here is we're going to build on top of what we had. So here we're using blue, and then here we have a base link. And our link, we have a new link here called right leg. So here we're going to be rotating 90 degrees about the y-axis and then shift down by 0.3 meters. So that's what this is for the origin. And we're going to make this one white. And then here we have a joint. So for our joint, we have a base to right leg. And then we're going to make it a continuous type of joint. And then here we define the axis to be about the y-axis. And then we have a parent link, which is our base link. And then our child link is going to be our right leg. And here we're going to be shifting the origin of the child link by this amount so that it goes to this side. So we could go ahead and run this now. So we come here and run this launch file, and this will allow us to view our joint. And you can see here we have a leg on the side. And then this here will allow us to rotate the leg about the y-axis, which is the green axis that we see. Now, finally, we could go ahead and take a look at a full robot example. So we'll be making a robot with 16 links and 15 joints. So below is a table that shows the 16 links. So you can see here we have cylinders, boxes, and then we split it up into the right and left side. We also have a gripper as well, and a head and a main box. And you can see the joints, we're connecting all the different parts together. So for the joints, we have the different connections, and we specify the different joint types. So you can see some are fixed, some are going to be continuous, some will be prismatic, and some will be revolute. So we could go ahead and run this example here by using our launch file. So this will generate our robot example and allow us to move the different positions with our joint state publishers. So you can see if I rotate this around, you can see this is our full robot, and you can see that all the frames show the different links and joints, and it goes to the positions as we want it to. And you can see here, this is our control center, which will allow us to move the different things. So this one here is moving the gripper. So this gripper here is actually using a STL file. So if you take a look at the file for this, the robot example, you can see this is our full example here. But the main thing that is different in here is that we have a mesh file name, which we talked about earlier, that will define our actual gripper. So you can see here, you could play around with the different controls and see how that works. So now I want to talk about Xacro files. So we just finished talking about URDF files, but what are Xacro files? So Xacro files you could think of are files that allow you to create functions that you can call inside your URDF file. So the main idea behind this is you don't want to have a lot of repeated code. So this will help simplify things and make your URDF much more readable. So let's go ahead and see how this looks like in VS Code. I will start off by going over the Xacro command, go over the robot state publisher method, the URDF launch file, and then talk about the Xacro property, Xacro macro, show you how to use a URDF using Xacros in the same file, and then URDF using Xacros in separate files. So to use the Xacro command, the way to use it is have the Xacro command here, followed by the macro.xacro and greater than model.urdf. So what this will do is take your Xacro file and convert it to a URDF file using the Xacro function. The next way to use Xacro is using the robot state publisher. So you could use this inside of your launch file. So for this, you need to have the path to your URDF. And then inside of your launch file, you could have a launch ROS.actions.node. We're going to use the package robot state publisher. And then the parameters that we'll be passing is a robot description. And we're going to be running the Xacro command inside of the launch file to convert our Xacro file into a URDF file. The third way is using the URDF launch package inside of your Xacro file. So inside of here, what we're going to do is call our find package share the URDF launch. And then inside of here, we're going to have a URDF package with the description of your robot and followed by the model name of your file. So let's talk about Xacro properties. So Xacro properties are useful when the same property shows up at multiple places. And this lets you change the value of all instances at one location instead of having to modify it all the places individually. So the way to declare a property is to have the Xacro property, and then name equals property name, and then the value equals some value that you set. So to actually use a property, you would put it somewhere inside of your code where you say variable equals, and then using the money symbol, the dollar symbol, and then followed by these brackets, curly braces, and the property name. So the Xacro macro, so here macros are used to replace several lines of XML code with the option of having input parameters. So this is useful when several lines of code are repeated inside of your files. So to declare a macro, what you're going to do is say Xacro macro, and name equals macro name, and parameters equals the list of your parameters. And then you have some logic in the middle, and then followed by the close Xacro macro. And to actually use this macro, you would say Xacro macro name, and parameter equals the value of the parameter that you want to set. So URDF using Xacros in the same file, we could take a look at this example file here. So we can see for our number 4 here. So here we actually could declare our Xacros inside of our files. So if we take a look at this file, we could see that in here, we have defined our Xacro properties up on top. And then, for example, this is a Xacro macro. So in this case, we're using this for a chunk of code for our inertial properties. And you can see if we want to actually use it, then we could find, the location that we're using this default inertia here. So you can see, for example, you could just call Xacro default inertial and then pass in the mass parameter. So that's how it looks like. And then if we go ahead and run this, we could see what is happening just to verify that it works. So I could run this launch command here, our launch file, and you can see that it renders our robot all working. So next up, we could use URDF using Xacros in separate files. So we could go ahead and take a look at the general structure. So we're going to have a separate Xacro file that has this structure here with the XML version, your robot, and you have to include this tag here for the Xacro. And then you might have some property and some macros inside of your Xacro file. And then using your Xacro file, so notice that this separate file is going to be called filename.xacro. And then inside of your main file that's using the Xacro file is going to be called something.urdf.xacro. And inside of here, to actually use the file, you're going to say Xacro include and then the file name, which is filename.xacro. So in this example, we're going to actually use our robot parts as the Xacro file that we're moving all of our macros in. And then our robot example, Xacro external URDF, number 5.1, that's going to be using it. So you can see here, we've used all of our macros here inside. So you can see we have different macros. We have a default inertia macro, we have a wheel macro, we have a leg macro, and then we have a gripper macro. So the reason we split up these macros is because we have a left and right for these different parts, and there's no need to repeat our code. So if we look at our example here, you can see that our example has been simplified by a whole lot because we use the property of symmetry. And you can see here we have included our file name. So just to take a look at a few, we have our default inertia here, and we have our different gripper, Xacro, and so on. So this really simplifies our code. So we could go ahead and run this just to verify that our new example is working. So if I run our launch file, you should see our robot show up. And you can see it behaves exactly the same. So we know that by separating our file into these Xacros, nothing has broken. Now let's talk about Rviz. So Rviz is a visualization tool in ROS that allows you to visualize the motion of your robot. It also has a lot of additional features that's great for camera integration. You could view the frames. There's like point cloud features as well. So we'll dive into how to use Rviz in ROS. I will show you how to simulate your robot in Rviz using the robot state publisher and our own state publisher. I'm going to go over the R2D2 ROS package, go through the Rviz configuration, talk about the URDF file that I'm using, review the launch file, go over the state publisher source code, update our setup.py, build our package, and finally run the R2D2 example in Rviz. So by the end of this video, we're going to see this robot here dancing around in circles. So I went ahead and created the ROS2 package using the ROS2 package create command, and we're going to add the dependency rclpy. Next up, we're going to talk about the Rviz configuration that we're using. So the point of this configuration file is that when you set up your Rviz environment and parameters or settings, plugins, you want it to remember what you set it to. So instead of having to set it each time, you're going to have the settings stored somewhere so that when you start up Rviz, you could just use it from those settings. So the specific things we care about is the fixed frame setting that we're using, as well as the robot model. And we want the topic to be coming from the robot description. And we also have the TF plugin set up so we could see the frames. So here is the file that has all the configurations. It's called r2d2.rviz. So when we actually call the command later, you're going to see we're going to be using this file directly. And some of this stuff will make more sense when we start up Rviz, so you'll see more details later on. So the R2D2 URDF file that we're using is pretty simple, but if you're new to URDF files, I have a video on it, so you could check it out. But the basic structure of our URDF file is we have a couple of links, the axis, leg 1, leg 2, body, head, rod, and box. And then we're connecting them with joints, leg 1 connect, leg 2 connect, tilt, swivel, periscope, and box connect. So we're going to link it between the parent and child links so that we can create the model that we showed earlier in the beginning of the video. Now let's take a look at our launch file. So our launch file is going to start up our robot state publisher and our state publisher. So we're going to call it demo.launch.py. And you can see right here, we have different settings. So first off, we're reading in our URDF file here. And then once we read it, we're going to pass it in later. So here we're going to store it as the robot description. So we have two nodes. The first node is the robot state publisher. And this we pass in our robot description. And then the second one is our state publisher here that we're using, which we will create our own and go through later on. So these two combinations will allow us to actually animate the robot in Rviz. So you can see here, this is our state publisher node that we created. So we've inherited from the node class. We called our node the state publisher. And inside of here, we do some things in terms of setting up creating the publisher here, as you can see, and we're getting the joint states. We set up a broadcaster, a node name. So these are all just some initial settings that we do. And then later on, we have a degree and loop rate that we're setting to. And we have the robot states, which we've defined here for the different angles that we're moving, the different joints. And then here on, we have a frame ID called the odom for odometry, and then we have the axis. And then here we have our main loop that does most of the simulation. So here we have a while loop that's going on. We get some clock time. We get the joint names that we're interested in. And then here we update the positions. You can see with the X and Y values as well as the Z, so X, Y, Z. And we have some rotation for a roll, pitch, yaw that we go ahead and update. So after we update everything, we want to publish the new states, and then we send the transforms. And then here we actually increment it by doing different plus and subtraction based on what we want the robot to be doing. And then finally, we place a little sleep at the end. And here we have an Euler to quaternion, as you can see, which we use here, and it's defined here, just doing the quaternion, Euler to quaternion conversion. Okay, and inside our main function, we're calling the state publisher node, and that will kick off everything and make it up and running. To get ready to build, we have to do some modifications to our setup.py file. So up here, we've added these imports because we need these modules later on. And we've added these two things so that we can find our launch file and URDF files. And finally, to use our state publisher, we've added this line inside our entry point. So to actually get our program up and running, you want to first build it, which I've already done. And then once you do that, you want to open up two terminals, one terminal to launch the launch file, and then the other terminal to start up Rviz2. So you want to cd to the directory, source it, and go ahead and run it. So I'm going to run one side for my launch file and then my other side for my Rviz. And you can see my robot here is up and running. So previously, we were talking about some of the settings you want to make sure your Rviz configuration has. So to actually see what those things that we were talking about, you can see here is a fixed frame. So you want to make sure that's set correctly. And you have the robot model, which we've added in. And you see the robot description here is robot description for the description topic. And these TF transform is what allows us to see the transformation. So now this is where things get more exciting. We're pretty much ready to do some more advanced simulation now. So with all the knowledge that we've learned up to now, we're ready to create our own simulation using Gazebo and ROS. So in this specific video, we're going to be using a TeslaBot robot, and we'll be integrating it in Gazebo. So we're also using ROS2 control as well. So the main idea is this. We have ROS2 control, which is responsible for the motor command. So the ROS2 control can be used to control position, velocity, or torque commands of the robot. And Gazebo is going to be the simulation environment that has realistic behavior such as physics. So you can have the actual weight of the robot to have a realistic torque estimation. And there's additional features you could add on, such as friction, to get even more realistic things. But for now, we're going to take a simplified case and just try to simulate the TeslaBot in Gazebo with a basic gravity setting. I'm going to start off by talking about how to install the Gazebo and ROS2 control packages, go through the package structure, talk about the coordinate frames that you need for your URDF file, go through the changes that you need to make for your CMake list and package.xml file, go over how to display your robot in Gazebo and the different things you need for your launch file, talk about the types of ROS2 controllers, go through the Gazebo and ROS2 control add-ons that you need to put inside your URDF file, go through the control YAML file that you need to set up your control parameters, and finally simulate your robot with the joint publisher. So by the end of this video, we're going to see the Tesla bot doing some air curls. To get everything set up, we need to install our Gazebo and ROS2 control packages. So here we have the different ones that we need. So just run these commands here. Now let's go ahead and create our package. So I made a package using the ROS2 package create command, and this is a general folder structure that we have. So there's a couple of new things that we've added. We added a new config folder. We added a new launch file folder. There's a new mesh folder, a URDF folder. So these files are also new ones, including the joint controller. We have the Gazebo launch.py. We have our STL files in here. We have our joint publisher that we've added, as well as our Xacro file for our Tesla bot. And then the two main changes we made are inside our CMake list and package.xml, which we'll go over later on. Now let's take a look at our coordinate frames that we need for our URDF file. If you're new to URDF files, I have a URDF tutorial in my channel, so go check it out. So here's a list of all of the joints that we're using. So we have the connection from the whirl to the head to the body, body to the shoulder, shoulder to the upper arm to the lower arm, and then finally the lower arm to the hand. So these are all the lists of the connections between the parent and child types. And then we have the type of joints where we have some fixed ones and some revolute ones. So all of the revolute joints you can see here are about the z-axis. So you can see here is a summary of the joints definition that I've made for the Tesla bot. And here is the Tesla bot Xacro file that we have right here. And you can see that here is just a bunch of links and joints to put together the robot. And all of the STL files are gathered from the meshes folder. Okay. Now let's take a look at the changes that we've made to our cmakelist.txt file. So the different changes that we make are the three things. One is to find the package, another is to create the executables for our joint publisher, and finally to copy the files to the desired directories. So let's take a look in here at the actual changes. So you can see these lines here is to include the packages that we need. Here is to create the executable for the joint publisher. And then finally, these steps here is to copy the files over. Now for the package.xml file, the changes that we need to make are to add the dependencies for our RCL CPP as well as our trajectory messages. So you can see that we've added these two lines over here. Now for our launch file, we need to add some things to display our robot as well as other actions. So we have a launch Gazebo, which will start up our Gazebo. We have a robot state publisher, which will publish the state of our robot for visualization. We have a spawn robot component, which will display the robot in the Gazebo. We have a joint state broadcaster, which will publish the state of the robot for control. And finally, the joint trajectory controller that will receive and control the robot joints. So let's take a look at our actual launch file here. So you can see here we have our includes up on top. And then here we're actually utilizing the Gazebo ROS package and then their launch file gazebo.launch.py. And then here inside we have a robot description. So this will parse our URDF file, the teslabot.urdf.xacro file, and store it inside robot description, which will we then pass into here for our robot state publisher. So that will get the information of our robot. And finally, this will spawn our robot by using the robot description for our topic. And then the next two steps deal with the ROS2 control. So one, we're both loading controllers, but one is for the joint state broadcaster. And then the other one is for the joint trajectory controller. So we just go ahead and run the 5 actions, and then we'll get everything up and running. So coming back to here, we can see that now to actually get everything up and running, what we want to do is build, source, and run the launch file. So a couple things to note is that sometimes if you see it not working properly, it could be because you didn't close your Gazebo. So you could actually force start it by running this command down here. So let's go ahead and open up our terminal, and we could just run the command. I've already sourced it, but you can see if I run the command here, gazebo.launch.py, we could see our robot spawn inside Gazebo. So it'll take a minute for it to start up, but you can see right here we have our robot inside Gazebo, and you could pan it around. You could use your mouse wheel to spin around like I'm doing here. You could zoom in, zoom out with the key, and you can also pan by dragging. Okay, so this is the robot model that we're using, and later on we're going to see us animating it. So to actually move our robots, we have to have a little bit of understanding of the different types of ROS2 controllers. So here is just to name a few, but the main thing you want to note is once you've decided the type of ROS2 controller, so you could control the effort, like the torque or current, you could control the position, the velocity. There's special type of controllers that are meant for wheeled vehicles called the diff drive controller. And these are just some of them out there. There's more things like PID control, admittance control, and so on. But here, the main thing you want to notice is that when you choose your controller, you want to make sure you know what message type that they're using, because later on, when we create our publisher, we need to send the messages in the correct format. So in our case, we're dealing with a joint trajectory controller. So here it uses a joint trajectory dot message. So this is the type of message that we're using. So later on, we'll take a look at how to actually format it properly. So if you want some references, you could check out the GitHubs here to have a better understanding of the different message types out there inside the common interfaces. So to actually get it working, you have to set up the Gazebo and ROS2 control in your URDF file. There's a certain section that you have to add inside of it, so I'll be going over that. But depending on the different type of controller you're using, you could choose different combinations of state interface and command interface. So the state interface allows you to read data, and the command one allows you to send data. So the different types of interfaces you're dealing with would include position, velocity, and effort. So here is the general structure of your URDF file. So you can see here, all of the stuff on top is going to include your links and joints. And then the key part that we're adding on to our URDF file would be the ROS2 control components. So here we have this part, the plugin that we've added. And then inside of here, you could have the list of your joints. So here we have joint 1, and then you could so on to list your joint 2, 3, and 4, however many you end up having. And inside of each joint, we specify the command interface as well as the state interface, which we'll show in a little bit. And then finally, you have the Gazebo component here, which will include our joint controller YAML file, which has the parameters that we're using. So if we go ahead and open up our file here for our URDF file, you could take a look at what's inside. So here inside of our Tesla bot Xacro file, if I scroll all the way down, we can take a look at our ROS2 control here. So specifically in this example, we have two joints that we're controlling. One is the arm upper to lower for the right, and then the one for the left. And you could set some parameters for the min and max angle for the joint. And then our command interfaces is going to be position. State interface is also position. And then we have two more here for velocity and effort. And we also set an initial value to be 0 here. Okay. And then for our Gazebo plugin here, this part is going to look exactly the same as we showed earlier. Now for our ROS2 control YAML file that has our parameters. So the general structure of this is you have one section that has the controller manager. And then here you have some update rate, the name of your controller in this section, as well as your joint state broadcaster. And then you have another section that will have the name of your controller and the parameters you're using, such as the joint names, as well as the interface names, command interfaces, and state interfaces. So here's a concrete example of the one we're using. So we've set an update rate of 100, and here's the name of our controller here, and this is the type of controller. And then the two joints that we're using, it's a left and right, upper arm to lower arm. And then finally, we have our command and state interfaces specified here. Now, to simulate our robot in Gazebo, we need to use the joint publisher. So for the joint publisher, the first thing we need to understand is the message types that we talked about earlier. So in this case, we're using the joint trajectory message. So here is the actual definition of the message. So you can see that the joint trajectory message uses the joint trajectory point. So if we take a look at that, the joint trajectory point includes position, velocity, acceleration, effort, as well as the duration. So we could take a look at our joint publisher file now. So here we created a node called joint publisher. And then inside of here, we created the name inside of here, joint trajectory controller, joint trajectory. So inside of here, we have the main thing that does all the work is the callback. So our callback function, we start off by making a message with the correct type. So notice that this right here has been included. So when we make the build, the files are made available to us because we've specified the dependencies. But here you can see that we have the joint names inside our message. So it's as a vector of just a bunch of names that we push back. And then here we have a point that we've declared. So the point is going to be a struct that contains the different information. So we have point.positions, and we push back the positions as like a vector. And then we have the start time, which we've defined. And then we want to push back the message, push back the point inside the message. And then finally, we print out our positions in this command here. So here we have our usual and our main function, the init, spin, and shutdown. Okay, so this is the main logic that actually controls the joints. So now to actually run it, we would have the previous terminal that we had up and running. So we want to have the Gazebo launch up and running. And then we're going to have another one that does the joint publisher. So if I go ahead and run that one, so this is going to be the terminal that actually causes the robot to move. So you can see now my robot is moving, and you can see the arms is moving according to the positions that I'm feeding it. So we just finished looking at how to simulate our TeslaBot using Gazebo and ROS to control. But what we're going to notice is that a lot of times when you're simulating things, you want to have a live plot of your data. You may want to visualize the joint trajectories or even the torque values as a function of time. Luckily, they have a tool called PlotJuggler. So I'm going to show you the steps and the commands you can use to set up your plots. So the agenda for today is we'll talk about how to install PlotJuggler, run PlotJuggler, plot the signal, save the plot layout, and load the plot layout. So by the end of this video, we'll see how the joint trajectories for the elbows will be plotted out in real time. So you can see this is what we'll see by the end of this video. So to install PlotJuggler, all you need to do is run these two commands. One is the PlotJuggler, and the other one is PlotJuggler-ROS. To run PlotJuggler, you could run it from the terminal using ROS to run PlotJuggler, or you can also put it inside your launch file here using the execute process, which I've done. So in one terminal, we could go ahead and start it up by running this command, which we introduced in the previous video, and then the other command to start up our joint publisher. So I'm going to go ahead and run that. So here, I've already sourced it. I'm going to run my launch file. So this is going to start up PlotJuggler. And they're known for, you can see this is our PlotJuggler here. And then in my second terminal, I'm going to go ahead and run the joint publisher. So this is publishing the joints. You can see my robot here is now moving, doing the curls. But now we need to actually set up some of the things for the plot. Okay, to set up the plot, you see here under streaming, there's a ROS Topic subscriber. So you have to click the start button. And then here you could choose the topic name that you're interested in. For me, it's going to be this one here. So I'm going to hit OK. And then once it loads, you could expand this, expand it again. And you're going to see under points, it's going to be the points that we're looking at. So if I pull this down, you can see more of the window. And you can see here is the positions. So you could go ahead and click on this and then drag it over. And this will plot the joints for one of them. And if you hover over this by the X icon, you can see here the vertical or horizontal split. I'm going to split it up and down. And then now I could drag my second signal here to see both joints at the same time. And you can also drag it in the same plot if you want to see two plot together. So if I drag position 1, you can see there's two overlay together. Okay. So you may be interested in saving this layout that we've created. So to do that, you could click these icons here. One is load, and then the other icon is save. So you want to click the up arrow, and then there's going to be a window that pops up. So this is the window, and you could go ahead and save it to the name that you want. Here I'm calling it 2joint layout, and it's saved as an XML file. Okay, so now if you actually want to use the layout that you saved, what you want to do now is use the other button. So this is a load button, and you want to click the layout that you saved and you hit open. And after you hit open, you're going to see a window that pops up. Start the previously used streaming plugin, and you're going to hit yes. and you're going to confirm the topic that you want. And once it's done loading, you see that your 2 plots are now showing. So this is great if you want to reuse your plot layouts without having to redo it every time. Okay, so now I'm going to show you how to integrate a camera in your Gazebo simulation. So this is great if you have any sort of image processing or computer vision tasks that you want to simulate. So let's go ahead and jump into VS Code and see how to set up everything. I'll be going over the camera model, talk about the ROS camera sensor in the URDF file, go over how to view camera and images in Gazebo, and view camera images in Rviz. By the end of this video, we will see how we could simulate the TeslaBot's POV in the simulation that we can see in this video right here. Now let's talk about the camera model. So here is the camera pinhole model. At the very bottom here, we have what's called the camera center. So the camera center has a coordinate frame attached to it. We have the x-axis, the y-axis, and the z-axis. So the x-axis here is pointing towards the object that it's looking at. So here we have an object here. This is in the world space. And then it gets projected to the image plane in a 2D view. So this right here, the green plane is called the image plane. And this plane is defined by the width and the height. And we also have what's called the field of view. So this field of view is going to be the angle that describes how much of the view that it's looking at. And then also we'll have different concepts later that we'll be using, which is the clipping plane. We have a near and far clipping plane, which will describe the region of image that we're actually looking at and extracting in our images. Now let's take a look at the ROS camera sensor URDF file. So the general structure of the part that you need to add to your URDF file is this region here on the left. So this is a general structure, and what you have is the camera reference here. So this is going to be the name of your link, and in our case, we're calling that head. So that's what you can see right here. We have this head, and then here we have the sensor name camera and type. So that's going to be the same. And then we have a pose, XYZ, RX, RY, RZ. So we'll explain how we get this value here. And then visualize, we set to true. Update rate is some rate that you want. And then here we have the field of view in radians. So here we're using 1. And then we have the format R8G8B8. So this is going to be the format for the RGB. And then you could change the different ones, but most likely you'll be using this one to begin with. And then we also have the width in pixels and the height in pixels. So here we're using 640 and 480. And then here we also have defined the near and far plane in meters. So we've defined it here as 0.05 and 1 for the far. So here we have the plugin name here. It's going to be camera controller, and the file name is going to be the lib-gazebo-ros-camera.so. And lastly, we have the frame name, which is going to be the name of your joints. And here we're using world to head. So that's all you need to add in your URDF file to actually get everything up and running. So now let's go ahead and take a look at how we derive the actual coordinate frames. So if we take a look here, we have what's called our world frame. So our world frame, we have the XYZ axis. So the first thing that we're going to do is look at our camera pose. This is our initial pose. So you can see here we have our x-axis right here. So this x-axis is the initial pose of our camera, and then later we're going to be modifying it. So if we scroll down, we see the first transform that we do is going to be this right here. So here in our transform, what we have is we have a rotation about the z-axis, which will allow the camera to be viewing in the same direction as the robot. And then we have a z translation upwards. So that's this part. This is the translation, and this was the rotation. So we have the translation that will bring it up to the eye level. So that's the main point of that. Okay, so if we scroll down one more time, we have our camera pose 2. So what we're doing here is doing an additional transformation. So this transformation here is a rotation about the y-axis of the camera, and this will allow us to view down so that we can see the hands. So that's what this component here is, 0.7. So now what we want to do is go ahead and view the camera and image in Gazebo. So what you want to do is run these steps here in one terminal. So we'll pretty much start the gazebo.launch file that we went over previously in our TeslaBot simulation. And then we're going to run in a second terminal our joint publisher that will make the robot actually move its arm. So let's go ahead and see that in action. So I went ahead and ran that, and you can see that here we have the robot arm moving up and down, doing the bicep curls, and you can see its POV here of seeing its own arms moving in this image plane down near the floor. So now we're going to go ahead and view the camera images in RViz. So what you need to do first is make sure you have the joint state publisher in your launch file. Otherwise, some of the joints won't show up. The fixed joints don't need it, just only the revolute. So you want to add this section here into your launch file, which is the joint state publisher node. So have that in there, and then it'll run the node to actually publish the joints over to RViz. So in the third terminal, what you want is to start up RViz. You could do the configuration if you have a configuration set up already, but I'll show you how to set up everything manually. So to do that, you just need to run the rvis2 command. And then here we also have the sudo to install the joint state publisher if you haven't already. So we're going to go ahead and run rvis2 here. So if we start up rvis2, you could see it starts up blank, and then what you want to do is add the different things here. So you can see we could add in our robot here. Our robot won't be moving. It's just going to be the model because we're not actually connecting the simulation here. But if you wanted to see the robot, you go ahead and choose the description topic and choose robot description here, and you can see our robot. And then if you want to see the image, you could go ahead and add in the image here. So here, if we scroll down, you could see here we have the image. And inside of here, you want to make sure you've selected the right topic here. So here you could choose in topic, there's a drop down, it's going to be camera image raw. And if we select that, you can see down here is going to be our image. You can see the image, the same scene that we saw in Gazebo. We just finished talking about how to set up cameras. Now we're going to talk about how to set up Lidars. Lidars are great because they could give you a dense point cloud of your scene, so it's perfect for 3D reconstruction, like for autonomous vehicles, or even for manipulation of objects. So here we're going to go over the steps I need to go through in VS Code to get that up and ready to go. We'll be talking about what is a LiDAR and how does a LiDAR work, types of LiDARs, Gazebo LiDAR sensor plugin for your URDF file, the LiDAR Gazebo simulation, and the LiDAR RViz simulation. By the end of this video, we will see how we can generate LiDAR in Gazebo on the left, and the same thing in RViz on the right. So what is a LiDAR and how does a LiDAR work? So LiDAR stands for light detection and ranging, and it works by sending light and determining how long it takes to reflect back a surface. So based on the time and speed of the laser, we can estimate the point in space. So here's a simplified model of what a LiDAR does. So let's say we know 3 parameters. Let's say x is the distance from the LiDAR to the point, t is the time to send and receive the light after reflecting, and v is the speed of light. So if we assume that this is x, and we assume that to go back and forth is going to be 2x, then we could approximate this as v times t. Since t is the total time, if we want to solve for the distance x, then we could do v times t divided by 2. So this is for a single point. You can imagine if you were to expand this to 2-dimensional or 3-dimensional, you would just have points in more than one direction. Now let's take a look at the types of LiDARs you may encounter. So we have the 1D LiDAR, the 2D LiDAR, and 3D LiDAR. So these are some of the common types you could see, but the main difference between these 3 types of LiDARs is the direction of the rays that it's shooting. So for 1D, you could just imagine you have something that points in only one direction. In 2D, you will have a LiDAR that's pointing in all directions in a single plane, as you can see here. And then in 3D, just imagine if you have something and it's pointing in all 3 directions like a sphere. So this could be good if you're trying to detect a whole environment and you're trying to reconstruct the entire scene, then you may want to use 3D. Or you could be smart with your 2D and kind of move up and down, and from there you could generate a 3D scene as well. Okay, now let's go ahead and take a look at the Gazebo LiDAR sensor plugin that you need inside your URDF file in order to see the LiDAR in Gazebo. So first off, we have what's called the Gazebo reference, and this is going to be the name of the link of your reference. So in our case, for here, in our previous videos, we're using head as our reference link. And then ray is going to be ray, and then the name of your LiDAR, you could just call it something. In our case, we're calling it LiDAR sensor. So the pose is going to be XYZ, RX, RY, RZ. So this is going to be some pose that you choose. For us, we're going to just choose zeros for everything. But if in your case, you could update that to something that makes sense for you. You could also choose a link that's already attached to the same LiDAR, or you could just transform it relative to some link that you have. So next up, you have the visualize Boolean here. So to see the LiDAR, you want to put true for that. And here we have the frequency in hertz. For that, we're going to do 10. And then here we have samples, which is going to be the number of points. Here we're using 720. The resolution, we're using 1. And then the resolution is going to be the scan resolution. So if you want to have more sparse, you could change that value or play around with whatever makes sense for you. And here we have the min and max angles in radians. Here we're doing a full circle, so we're using negative and positive pi. Next up, we have the min distance and max distance in meters. Here we're setting it to be 0.1 and 30. And then we have resolution in meters. So the resolution in meters, we're going to set it to 0.01. And then finally, we have our plugin. So the plugin here is going to be the name of your plugin. So here I'm just calling it LiDAR. And the file name that you're actually going to be using is going to be called libgazebo ROS raise sensor.so. So this is going to be the same. And you could choose different ones depending on which LiDAR sensor you're using, but here for the simulation, we'll be using this one. Now let's go ahead and take a look at how to see our LiDAR in our Gazebo simulation. So I went ahead and already built it, and then I'm going to go ahead and run my Gazebo launch file from our TeslaBot simulation. So this is going to pull up our TeslaBots with the LiDAR scanners, as you can see here, all the light rays shooting radially outwards. So you can see if I zoom out, you can see it's a giant circle. But if I go back in, you're going to notice that right now, all the rays are still uniform because it doesn't see any objects. So if I go ahead and drop a sphere in here, and then if I go ahead and scale it, so I could hit this button here to scale, and then I'm going to make it a little bit taller so you can see that it's going to start blocking some of the rays. So here, later when we get into Rviz, we're going to see the same contour line that's being intersected by the rays. Okay, now let's go ahead and see how we can see our LiDAR simulation in Rviz. So by default, the LiDAR will output points using the topic LiDAR out, where LiDAR was the name of our plugin. So by default, Rviz will use the point cloud 2, but if you want to use laser scan, you could go ahead and modify the plugin in our URDF file like this. So the main thing is you could have an output type specified here. So let's go ahead and see the LiDAR in Rviz. We could just go ahead and start up Rviz here. So type in Rviz 2, and this will launch another window that will show us everything. And if you want to see your robots, so you could have like a relative direction, you could go ahead and choose your robot model here. And then we want to come down here, and then inside of here is the description topic, and you want to choose the robot description. And this will show us our robot. And then if you want to see a point cloud, you could come here by topic, and you can see here is our point cloud 2. And you can see it shows up the contour. And you can see the topic here by default is LiDAR out. So if I go ahead and move this, you can see that this is my contour as we expected from our Gazebo simulation. Another very important sensor that I want to talk about is the depth camera. So depth camera is great because it can help you do things like depth estimation, but more importantly, it could handle things like 3D reconstruction if you're trying to reconstruct your scene from a depth map. So here I'm going to show you step-by-step in VS Code how to set that up. In this video, we're going to see how we can use the Gazebo simulation of our TeslaBot to look at a sphere using a depth camera. And then we're going to see it in Rviz to visualize the point cloud, and then also see the depth map as you can see on the bottom. I'll be going over what is a depth camera, talk about the ROS depth camera Gazebo sensor setup for your URDF file, talk about the depth camera frame orientation, which can be pretty confusing, and talk about the Gazebo depth camera simulation, and finally show you how to set up everything in Rviz to see your depth map and the point cloud. So what is a depth camera? A depth camera uses 1 or 2 cameras. So here we have a right and left camera. And usually there's something that we call the IR projector. So what this does is it's going to project some IR dots. And sometimes if it just uses 1 camera, it can be enough to detect the location of those points. And since you have 2 points of view, you could figure out the disparity between the left and right image. And then from there, you could determine the depth using some similar triangles. And from the depth, we can finally determine the point cloud for the scene. So here is an example of a Intel RealSense depth camera, the D435. So here you can see this is a general structure of the camera, and some important parameters would be like the base length. You need to know the distance between your cameras, and then you have what's the focal length, because when you have a camera model, you have some focal length that will project your scene to your image plane. So that's the general idea. You could have like an object here, and this object is projected in your image plane. So I have a video where I talk more in depth about understanding depth maps with OpenCV, so you could go ahead and check out this video for more information. So now let's take a look how we could set up our depth camera Gazebo sensor for our URDF file. So previously we used our head to camera transform in the Gazebo section, but now we're creating a new joint for it, and we'll explain the details of that later on. So we're changing this pose, which took care of some of the transforms, and now we're setting the pose to be all zeros. And then we're going to be creating 2 links. So we have one link here called the camera link, and then another link here called the camera frame link. So we're going to have 2 joints. These joints will connect the different pieces. So we have the head and then the camera link. So we're making a joint to connect the 2. And then here we're doing the transform that we did previously here. So we're moving this transform that we did previously to this. And then we're creating a second joint called camera link to camera frame link. So this will do the transform between these 2 links. And then this is going to be the transformation that we're going to be applying. And in the later section, I'll talk about the details of what that actually entails. So if we take a look here, the Gazebo URDF file for the depth sensor is going to be very similar to the camera sensor. So I talked all about it in this video, my camera, Gazebo, and Rviz video. So if you want more information on how we set up the camera, you could check out that video. But here you can see this is the part that we need to add inside our Gazebo file. So you can see here we have the camera link, and then we have the camera. And here's the main part that we changed is now the depth type. So this will enable our depth images when we're in Rviz. So I updated some things like the horizontal field of view, and then I also played with the clipping because I want to see a broader range. And then here I just renamed some of my plugins. And the key part you need to add here is actually the frame name. So this will associate your camera frame to the right link, which will take care of some of the transforms that we did previously. So let's take a look at the camera frame orientation. So below shows the transform between the camera link to the camera frame link. So initially, the camera link has the x-axis pointing in the direction of the camera. So you can see here is the x-axis, and it's pointing in the direction of the camera. But we want to find our camera frame link. So this will describe the camera frame, which is how typically the camera is oriented when you're actually going to display the point cloud. So we're going to do a series of transforms. So the first one is a rotation about the x in the negative pi half direction. And then that's our first transform, and this is going to rotate our z-axis. So now our z is pointing to in this direction, and y is pointing down. And notice that we're doing about the original x-axis, and then we're doing a second rotation about the z-axis in the negative direction of pi halves. So you can see now our x-axis is pointing to the right. So this is our new x-axis location. But the key point is to have the z-axis pointing in the direction that the x-axis was pointing in. So this is what we're expecting the camera link frame to be oriented. So if we scroll down, you can see that here is the view of the expected resultant frame. So you can see that the final orientation is the Z, and that's the expected orientation of our camera frame. And you can see X is pointing to the right, and then our Y is pointing down. So if we don't do these transforms, our point cloud is going to be all messed up, and it's going to be like upside down, and the sphere will be this way. So if you do all this correctly, then you should see your sphere in the right orientation somewhere on the floor. So now let's take a look at our Gazebo simulation. So we're going to set up our scene so that when we're in Rviz, we could actually see something in Rviz. So go ahead and go to your workspace, build it, source, and then run the launch file that we talked about in our TeslaBot simulation in our Gazebo tutorial video. So after you run that, you're going to see the TeslaBot simulation here inside Gazebo. And you could just throw in a sphere like this, and that will set up our scene to view everything in Rviz when we actually set up everything. Okay, now let's take a look how we can set everything up in Rviz to see the depth map and point cloud simulation. So in the terminal, you just want to run your rviz2 command, and then here you can set up everything. So initially, there's nothing, and then when you hit add, you're going to see an Rviz window pop up. And what you could do is double click this for the point cloud, and the point cloud will show up. And if you want to see the robots, then you want to add in the robot here. So if I scroll down, you can see the robot model. And if you double click that, what you want to do is choose the right topic, which is the robot description. And you can see our robot is now showing up. So this is our point cloud that we're expecting. The orientation is all correct because we set up the frames correctly. So now we could go ahead and add image here. So you could also view it from here. So under depth image raw, you can see image here, and you double click that. You can see this is our depth map image here. So this is pretty nice if you want to use that for something later on. But we can also see in our Gazebo simulation, if I pull that up, you could also play around with changing the location and seeing the different things move around. So here you can see I have the ball, and if I drag it, then you can see the depth map here and the point cloud updates, which is what we expect. So it's nice to see everything moving dynamically. All right, in this video, we're going to show you how to simulate a mobile robot using Gazebo and ROS to control. Specifically, we're going to be using the Cybertruck, and we're having our TeslaBot ride the Cybertruck because the TeslaBot can't walk yet, so it's going to be riding along, telling it what to do. So if you haven't seen my TeslaBot simulation, go ahead and check out this video right here. But in this video, we'll be covering these topics here. So we'll be talking about how to do the Gazebo and ROS to control installation, the package structure, the CMake file changes, the coordinate frames, the URDF file, the Gazebo and ROS to control launch file, the Gazebo and ROS to control setup for the URDF file, the YAML file for the diff drive controller, and the command publisher to send the commands to wheel robot, and finally go over some visualization of the data with PlotJuggler. So to get Gazebo and ROS to control setup, make sure you go ahead and run these commands to install everything that you need. So here's a package structure for our Gazebo simulation. So if you haven't made your package already, go ahead and run this command here to make your package. But the structure for our folders is right here, as you can see below. So we're going to have a new folder called config. And inside of here, we're going to have our YAML file. We're going to have a new folder for our launch file, and then make our own launch file here. We're going to have a new folder for our meshes to contain our STL files. We're going to have a new file called the diff drive publisher.cpp. And we're going to have a URDF folder that contains our Xacro file. Make some changes to our CMake list, and then just leave our package.xml alone. Okay, now let's take a look at the things we need to modify in our CMake list.txt. So up here, we have our find packages. We have one for our ment CMake, our geometry messages, and our RCLCPP. And next up, we want to include our directories. We have our launch, URDF, config, and meshes. And we want to add our executable here. So we have one for our diff drive publisher, which will be sending our commands. And then we have our target dependencies set up here to use these two things. And finally, we have our install targets, which we're including our diff drive publisher, and have our destination here. Next up, let's take a look at our coordinate frames for our wheeled mobile robot. So here we have 4 wheels. You have the first one, the second one, the third one, and the fourth one. So these 4 wheels, we have our coordinate frames. I'm drawing it XZ, the Y-axis you could figure out by the right-hand rule. But all of these we have shifted here. So you can see these dots here is the actual location. I'm just drawing the frames on the outside for better visibility. And you can see our Tesla bot here is right at the center of our Cybertruck. And we have some key dimensions here are 1.146, which is the separation of our wheels. And then this value here, 0.4175, is the radius of our wheel. So if we scroll down a little bit more, you can see this is the top view of our, or the side view of our robot and our Tesla bot, the truck and the Tesla bot. So you can see some of the key dimensions here that we care about is this dimension here, the 1.5. So this is the distance between the center and the wheel in the X direction here. And then we have another one, a very small distance here, which is the Z shift of the wheel relative to the center. And then we have another dimension here that's going to be the distance from the robot to the base of the body of the car. So these will be some key dimensions that we'll be using later on in our URDF file. Okay, so now let's take a look at our URDF file for our wheeled mobile robots. So here are the lists of links that we're going to be going over. We have the body, window, the front left wheel, front right, back left, and back right. One thing to make note is that you need to make sure you have your collision tag. Otherwise, the wheel is just going to sink through the ground and your robot's going to disappear. And here are the lists of joints that we're having. So everything is going to be connected to the body. So we have to make that joint connection to allow it to rotate later on. And one thing to note is that the direction of the axis needs to be flipped, because previously when we were looking at our wheels, we have one wheel, we have the Z-axis pointing outwards. So because they're pointing outwards, we want it to rotate in the same direction. So you have to flip the direction for the axis. So if you want to have a more in-depth review of the URDF file, I have a video right here, so you can go ahead and check it out. But let's go ahead and take a deeper dive in our Cybertruck URDF.Xacro file here. So here is the URDF file, as you can see here. So we're going to take a look at that. Up here on top, what you can see here is we have our body. And for the inertia, the inertial tags, I'm not really caring about that right now. You could fill it out to be more accurate later on. But the key part right here is we're adding a mesh for our body. So we have a body.stl file here. And then we're going to just leave the scale to be 1:1 because I've already set up the scale correctly. And we scroll down a little bit, you see we have our window. So the window is just something I created so that you could see the windows in different colors. And again, it has its own window.stl file. And then next up, we have the front wheel. So for our front left wheel, what we have is we just have some filler here for the inertial tag. But the main important part is going to be the collision. I made the collision tag to be very similar to the actual size of the wheel. And then again, I have a wheel STL file. This wheel STL file will be the same for all of the wheels. So I'm going to repeat the same thing for the front right. And we have the back left. Again, let's repeat it. And then you have our back left here, back right. So all of these will be pretty much the same. The main thing that's going to be changing is going to be the actual joints. So if we take a look at the joints, the different things that we're actually modifying here is these values here. So if we take a look at this, you can see the key part is going to be the origin. So if you notice here, some of these values will be different. So you can see that this one is going to be positive and this one is negative here. Because if you look at our coordinate system previously and the y, one is in the positive, this one is in the positive y, this one is in the negative y. And then here we have the same thing. Now we're shifting it to the back. So here we have negative x with positive y, and then we have negative x with negative y. So these are the combinations to put the wheels in the right direction. And then we have some rotation here. We have a negative pi half, a positive pi half, negative pi half, and positive pi halves. So these will allow the direction of the axis to be pointing with the z-axis outwards like we saw in the coordinate frames earlier. And then finally, we have our continuous tag. So this will just allow it to be rotating. So that's one of the key parts. And finally, we have our axis here. So notice that we have in the positive Z and then negative Z, positive Z, and negative Z. So this will allow the directions to be in the right direction as we talked about earlier. And then finally, each one we have a parent and child. So that's going to tie the body to the correct wheel. Okay, now let's take a look at our launch file that we need. So the main things that we have a Gazebo launch, a robot state publisher node, a robot spawn node, a joint state publisher node, a load joint state broadcaster, a load joint trajectory controller, and finally a run PlotJuggler. Okay, so here you can see that these are all the imports that we need to have everything up and running. And the first thing that we have here is you can see we have our Gazebo launch. So this will start up our gazebo.launch.py file. So this is the core thing that we're calling, and we're calling it from our package here called Gazebo ROS. And this will start up our Gazebo. And you can play around with world files here if you want to. And then right here we have our robot description. So this will read in our cybertruck.urdf.xacro file, and then it's going to use the Xacro command here and pretty much extract everything and convert it to URDF file. And then we have a robot state publisher here, so this will get some of the joint informations that we'll need for our simulation. And we scroll down a little bit more, we have some things for the Rviz. So you can see right here we have our joint state publisher node. So this will be the things that will show the things in Rviz when we actually try to render it. And then we have a robot spawn node. So this will actually get some of our robot description information. We have a load joint state broadcaster. So this is some of the things for ROS2 control to make some of the commands available. And then finally, we have these last two things. So here we have our load diff drive base controller, and this will get some of our commands for moving the wheels. And we have our run PlotJuggler, so this will help visualize some of the things. So tying it all together, we have our launch description here. So we're gonna just call all the things that we've created up on top and then return it as a launch description. So now if we run this ROS2 launch wheeled robot gazebo.launch.py file, we're gonna see the rendering of our robot show up here. So you can see that this is our Cybertruck here, all nicely rendered. You can see we have the robot up on top of the car as we expected, and you can see that it's a nice color that we've set, and we'll go over some of that later on. But right now everything is not moving yet. We could just see the simulation of it, but after we start sending the commands to everything, you could see the wheels moving, and you can see the nice texture on the wheels. It's black right now, so you can't see all the details, but you could play around with the lighting and the colors if you want to see more details later on. But you can see it's a pretty nice rendering here in Gazebo. Okay, so now let's talk about some of the tags I need to add in our Xacro file so that we can actually use the ROS2 control to move the robot. So here we have the ROS2 control tag here, and what we want to have is a Gazebo system, and type is system. So in here we're gonna use our hardware. So we have our Gazebo ROS2 control Gazebo system. And then we want to set up the joints that we're actually going to be using to be moving. So this is going to be a rear wheel drive Cybertruck. So we're going to have one joint name here. We have the body to back left wheel. We're going to be commanding it in velocity. And we're going to be using our state interface to be monitoring the position and velocity. And then similarly, we're going to be doing this for the right wheel. And if we scroll down, we're going to see that we have our Gazebo tags here. So these are some of the things I need to pay attention to. So here we have our Gazebo tag here. So this will use our Gazebo plugin. It's going to be called libgazebo ros2control.so. And the name is going to be called Gazebo ros2 control. And here we're getting the parameters from our diff drive controller.yaml file, which we'll be going over later on. And this is going to be located in our config file. And then here we have our Gazebo references. So some things to note is that once you set this up, you can set the colors, and then for each of the wheels, you get to set also the colors for the wheels, but also two main things you want to make note of is that we're actually setting the mu values to be 0. So we want the front wheels to be just passively rotating since they're not being driven. So these would be the key things you want to add to make sure that it's not interfering. So make sure you have those friction parameters set. And we have our mu1 and mu2. So mu1 is the main direction and mu2 is the perpendicular direction. Okay, so that's what the mu1 and 2s are for. And if you scroll down a little bit more, you see that we have The same thing for the back and the back left and right wheel, except those are driven, so we're just not going to set a mu value for that. And then some of the Tesla bot things I went over previously, so I won't be going over that. Go ahead and check out that video if you want to see more detail. Okay, now let's take a look at our diff drive controller YAML file here. So this YAML file will allow us to set some of our configurations for our robot control. So the main things we want to make note of is we want to set our left wheel names, right wheel names, the wheel separation, the wheel radius, and the base frame ID. So right now we're only using 2 wheels, but if you want to use 4 wheels, you could set it as a list here. So you can see here we only have a list of 1 for each. And some things to make note of is that you want to set right here the joint state broadcaster, and then we have our diff drive base controller here. So these are the controllers that we're going to be using. And then we have our wheel separation here. Our wheel per side is going to be 1 here, and we have our wheel radius to be 0.4175, which we know from our STL file. And we scroll down a little bit more. Some of the key things to note is that we have our ODOM. Frame ID is called ODOM, and our base frame ID is called body. Okay, now let's take a look at our diff drive commands publisher for our wheel mobile robot. So we will be controlling our mobile robot with a twist stamp message through the diff drive base controller command velocity topic with our own diff drive publisher. So we have a series of different message types that we'll be utilizing. So let's take a look at that. So you can see here we have a twist stamped message. So here we have a twist that's going to be a type twist. And then from there, we're going to be using from the twist message. So inside the twist message, we have a vector 3 for both linear and angular. And then what a vector 3 is, it's going to be defined in the vector3.message, which is going to be float 64 of XYZ. So essentially, you're going to have XYZ for the linear and XYZ for the angular. But one thing to note is that because our robot is in a plane, what you're only going to have is going to be a linear X and then the angular Z to control the left and right. Because in practice, a car, you imagine you have a car here, you can only go forward, and then you could turn right or turn left, and that's going to be controlled by the angular Z. So really, even though a twist stamp has 6 values, we're going to be using 2 of the 6. So now let's take a look at our diff drive publisher file. So here we have our file that's going to be sending our commands. So here we have some of our includes, and we've created our class here called diff drive publisher. And inside of here, we're going to make our node. And then once we make our node, we're going to create our publisher here. And then we have our topic here set up with our certain frequency. And then we have our callback here using our timer, create wall timer. And then finally, we have our private here called publish command. So this publish command here is the main thing that we're going to be using. We're going to be sending a linear.x at 0.1 and an angular.z at 0.1 as well. So this will allow it to the robot to start rotating while going straight. And then finally, we have some other private variables that we've declared here. And then we're going to call our typical init, spin, shutdown, and then get everything up and running. Okay, so in one terminal, we had our Gazebo launch file running. And then in our other terminal, we're going to run our diff drive publisher here. So this will actually make our robot start moving. And if you can see here, if I open this, you can see our robot is rotating as we expect. So if you zoom into wheels, you can see the wheels are turning. And this one's turning forward. And the other one is also turning forward. But you can see this one is turning a little bit slower as expected, since we're actually having it rotate, so you would expect one wheel to be turning faster than the other wheel. So from the top view, you can see that it's starting to curve, making an arc. And this is exactly what we expect the motion to be. And you could play around with the different speeds to see if it could go faster. You could also make it negative to go reverse. You could change the direction of the angular Z to make it turn left or right based on whatever you want. So you could play with that and see what suits your needs. But you can see right now that everything is up and running. You could also try adjusting the mu variable, and then you'll see that the front wheels will have issues because of the friction. But you can see right now it's just not rotating, it's just sliding, but that's okay. Visually, you can see that because it's still performing like we want it to, then it's pretty good. Now, you may be interested in visualizing the data in PlotJuggler. So I have a video that I posted recently here, so you could go ahead and check it out for some of the details. But what we're going to do is just show you how to visualize some of the data that we've already set up. So If you go to the layouts, I've already saved the layout. And again, I went over this in that video. But once you upload the layouts, you get to see that we have some of our topics that we've chosen here, the ODOM and the joint states. I'm going to hit OK. And you can see that our plots will be showing. So here you can see these are our wheel velocities. You can see that the green is the called body to back left, and the orange is the body to back right. And you can see that there's a difference in terms of the magnitude. So the orange one is higher and the green one is lower, which is as we expect. So that just means that one wheel is turning faster than the other. And this right here is an XY plot that I've also generated. So this is showing you the trajectory of the mobile robot, in this case our Cybertruck, as it's moving along in a circle. So this might be useful if you want to do some analysis on the trajectory. In this video, we're going to be using our Cybertruck and the SLAM toolbox in ROS to create a map of our environment by driving the robot around. We'll be talking about what is SLAM, how to install the SLAM toolbox, how to set up Gazebo world, how to run SLAM toolbox and set up the parameters, how to set up Rviz settings, how to run the Rviz from the config file, how to handle this special error that you might be seeing called no map received, and how to create the map with SLAM toolbox, how to save the map, and finally how to load the map. All right, so what is SLAM? SLAM stands for Simultaneous Localization and Mapping. So that's the acronym for SLAM. And the main question that we want to answer is, where am I? So to figure this out, you could break it up into two parts. First, we want to find the map of the environment. That's the mapping part. And the second part is location of the robot relative to the map. So that is considered localization. So with simultaneous localization and mapping, we're actually doing both of these things at the same time. So there are three main frames that we want to consider in ROS when we're dealing with SLAM. And the first one we want to look at is ODOM. So what the ODOM frame is a fixed frame of the robot starting location. And the main properties of that is that it's continuous and smooth, but one of the main issues is that it can drift. So drifting means it might go somewhere over time and it's not any longer accurate, no longer accurate, okay? And then here we have the map. Map is a fixed frame of the robot's starting location, and it's the map's origin. So some properties of that is it's discrete, but the thing is that it's relatively accurate. So that's why we want to rely on this map. And the base is the location of the robot. So in the perfect world, we can map the environment using our odometry, which is our wheel encoder, and our Lidar point cloud. So as the robot moves, we'll collect the point cloud. And the ODOM and map frames would be coincident. So if we look at this image here, this is a perfect scenario, okay? So if you imagine the robot is moving around, so here it moves to like position 1, and it gathers this point cloud data. It moves to position 2, and then it gathers this point cloud data here, and then it moves to position 3 and gathers this point cloud data here. So you can see that the point cloud data perfectly aligns with the wall. So here it's inside a rectangular space, and it's going to be perfectly capturing the data. So in the perfect world, the ODOM and map frame is going to be coincident, and it's going to be at the location where the robot started. But in practice, drifting happens. So what we're actually going to be seeing is something like this. Okay, so in practice, we're going to be seeing drifting. So what that means is, you have your map frame and the robot moves to some position, but maybe as it moved there, the orientation kind of got lost. So instead of having the point cloud map exactly where the wall should be, it's maybe slightly at an angle. And again, it might move to another position, and you can see that it's not perfectly aligned with the wall. And it moves to another position, and you can see it's off again. So this is the cause of drifting. And what ends up happening is that, let's say by the time the robot returns home, the ODOM frame is actually going to be in some position that's no longer accurate. Okay, so you can see that it's been drifted away from the map frame, and it's going to be causing some error. So this is why we have SLAM. SLAM is used to correct for these errors and uncertainties, and by using the Lidar and odometry and computer vision optimization methods, we can more accurately estimate the pose of the robot. So the whole SLAM pipeline, you could think about it as these steps here. So you have sensor data as the input, and then you could think of it as breaking it up into two parts. You have the front end and back end. and the output is going to be your map. Okay, so the front end is going to be things like feature extraction. You have things like the different fast, sift, orb, and serve. I have videos on that. You could go ahead and check it out. You have the feature matching part, which I also talked about in some of my OpenCV videos. And then here you have the determined transform of the camera or the robot, because typically the camera is going to be on top of the robot. And then next up, we have the backend. So the backend is the key part is the optimization. So you gather all of these things. So previously for the front end, we're talking about consecutive frames. So between like each segment, something happens. But the backend looks at everything all together and tries to minimize the error of everything. So there's methods like the extended Kalman filter, particle filters, least squares, the graph, post-graph optimization. Typically, they like to put it in graphs for data structure because it's more efficient. So once you have that, the idea is you want to break up the map into discrete cells, and the SLAM algorithm could determine the probability of the cell, being either occupied or empty. So occupied is going to be black, and empty is going to be white. So here's an example of the map that we'll be creating later, and you can see the black spots. As you can see, black was occupied, right? So black is usually going to be some obstacle. So in this case, our obstacle is our wall. So black is like the estimation of where the wall could be, and all the white spaces is the parts that is just free space, okay? Okay, so how do you install the SLAM toolbox? So to install the SLAM toolbox, it's pretty simple. You want to run these two commands, the sudo apt-get update and sudo apt install ROS, and your distro plus the SLAM toolbox. Then everything should be up and ready. Okay, so now we're going to talk about how to set up the Lidar for SLAM toolbox. So we will discuss how to add the Lidar in your Xacro file. So first we need to add the Lidar link and transform it so that the Lidar is in the correct orientation. Otherwise, the object will appear to be on the left when it should be in front. So here's the part you need to add to your Xacro file. We have a link name called Lidar link, and we're going to be combining the head and Lidar link together with a joint called head to Lidar link, okay? And for our rotation, we're going to be adding a pi halves here. And later, we need to add something else for the sensor message. So you want to make sure that the message type is the correct type, and that type is called sensor message, and it's going to be laser scan. So you want to add this part too to your Xacro file for your plugin. So previously we've had this, but the part you need to add is this part. The output type is going to be the sensor message laser scan, because the SLAM toolbox is expecting this type specifically. Okay, so now we're going to talk about how to set up Gazebo world for the SLAM toolbox. But before SLAM toolbox can work properly in Rviz, we need to make sure that the Gazebo world has objects in it. Otherwise, it won't work. The Lidar needs to detect objects and pass that data to SLAM toolbox. So here is the part that we want to add inside of our launch file. So this is how you could start up Gazebo. This is how we started up previously, but the main things that we've added is this part here, which is the launch argument. So inside of our launch argument, we have a config, and we've created a world file called walls.world. And another thing that we've added is the use sim time is true, which we're adding for everything else inside of our launch file. So that's the main thing we've updated. And to actually see the world, we're going to be going through the steps where we cd, Colcon build, and then source, and then run our launch file. So I'm going to go ahead and do that. So here I've already built it. I'm just going to run it. And this is going to go through the process of everything. So I've already got Rviz set up. We'll go into that later. But here you can see our world. So this is our world that we've set up, and you can see the walls, okay? Okay, so now we're going to talk about how to run SLAM toolbox and set up the parameters. So first we need a copy of our parameter file, which could be found from the following path here. And then there's a couple of things to note. There's two terms that's being used as online and asynchronous. So online just means it's running in real time, and asynchronous just means that it's going to process the latest data, and then everything's going to be running in parallel, but some of the data might be skipped. And we need to make sure that the parameters in the parameter file, which is called mapper params online async.yaml, is set up correctly. So the main parameters that we're going to be touching are these part, the ODOM frame, which we're calling ODOM, map frame, map, base frame, which I'm calling body here, and then our scan topic, which is the default name that the laser Lidar that we're using, which is Lidar out. So some applications may require a robot footprint frame, which we're not using, but you could go ahead and look that up if you need it. Okay, so a couple ways of to run your SLAM toolbox. To run it from the terminal, you go ahead and run this command here, ROS to launch SLAM toolbox online async launch.py, and you want to pass in your parameter file. One thing you want to note is it's called SLAM params file, and just specify the location of the parameter file and say use sim time is true. And you could do the same thing using it from the launch file using this these few lines of code here. And then when we start RViz later, we should be able to see if our SLAM is working properly. Okay, so now we're going to talk about how to set up your RViz settings. So here in the global options, what we want to do is make sure the fixed frame is set to the map frame. And then the next up, we want to look at the laser scan. So for the laser scan setting, you want to make sure the topic is Lidar out here. And next up, you see the map. So the map, we have map here for the topic. Make sure that's set correctly. And then we scroll down a little bit. We have the robot model here, and you want to make sure you have the robot description. And then lastly, we have our transforms, which you could turn on and off as needed. And make sure you set all of these in order because it's going to matter, okay? So how do you actually start RViz from the config file for SLAM Toolbox? So in RViz, we've went ahead and saved our RViz file into this path here. And then if you want to run RViz from the launch file, you could go ahead and add this part to your launch file. Okay, so how do you handle the no map received error from SLAM Toolbox? You may see the following error here. No map received, and at the transform, it says could not transform from blank to ODOM. So the list of things you want to make sure is that all of these things are happening in order because especially if you're not using a launch file, then you may do these steps out of sequence. So some part of the pipeline might be expecting data and it's not seeing it. So first off, make sure Gazebo is running, and then there's objects in Gazebo. Once you have all that, you could run your Slambox toolbox. So this will actually start up the map topic. And later on, when you actually open up RViz, then you could finally set the fixed frame to map. Map should show up only after the SLAM toolbox is showing. And then the laser scan should only be able to pick up stuff once there's objects in Gazebo. And then finally, you could set up the maps to start visualizing the map. Okay, so hopefully if you follow all these steps in the right order, you shouldn't see any error that says no map received. Okay, so how do you create the map with SLAM Toolbox? So to create the map, we need to drive the robot around. And to do that, we're going to be using the teleop. But before that, you need to make sure that the diff drive controller.yaml file has the use stamp velocity here set to false. So go ahead and update that file. And then now we could run the teleop to move the robot around. We're going to be using the ROS to run teleop twist keyboard. And then we're going to be using the command velocity called the diff drive base controller command velocity unstamped. Okay, so it's only going to work with unstamped, so make sure that you have that set up correctly. So now that we have that set up, we go ahead and open up our terminal, and we're going to have one terminal that's going to run our launch file, and then in our other terminal, we're going to go and run the teleop. So this teleop will let us use our keyboard here. So once I run that, I'm going to pull this over to another window here. And then here we're going to set up the Gazebo and RViz side by side. So this will allow us to compare it and see what's happening. So now we're just going to go ahead and drive the robot around. So here you can see that initially it's facing like the X direction. So we're just going to rotate this so it's facing in a similar direction. Okay, so now that you can see both views, we could go ahead and start driving it around. Okay, so now that we finished driving around, you can see that it created a pretty good map. It's pretty square. You can see there's some parts that's not quite perfect. The overall orientation is a little bit rotated, but I would say relative to where the robot is, if you look here, it's actually pretty accurate in terms of the relative location. So if we take a look at the actual frames, we could come here to TF and we could actually show it. But here you can see that if we zoom in, you can see that here is the ODOM frame. So you can see ODOM drifted quite a bit. I think it seems to be more sensitive to when you're actually rotating. And then here is the map frame, which is the center of our map. But in terms of the overall map shape and the relative location of the robot relative to the map that's generated, I think it did a pretty good job. You can see that there's some parts here that's not quite good, like on the right, but I think overall I think it does the job. Okay, so how do you actually save this map that you want and then reuse it later? So what you want to do is come here to Panel and then Add New Panel. Then here you're going to see the Slam Toolbox plugin, and then you hit OK. And then down here, you could actually just write the name of your map. So you could write map as your name, then you could hit the Save Map and then Serialize Map. And then once you do that, it's going to go ahead and save it to your file folder in your root ROS2. So if we take a look here in our file structure, you're going to see that it should have created these files here called map.data, map.pgm, map.postgraph, and map.yaml. So the main thing to note about these files is that there's different functions. PGM is a cell occupancy data. The YAML is the grid resolution and origin location, the stuff like that. The map.data is the data from mapping, and the postgraph is for some of the optimization stuff. So for me, I'm going to be putting it into the config folder, but for you, you could put it wherever you want. Okay, so now that we've saved our map, how do you load the map from the Slam toolbox? So first thing you got to do is update your mapper params online async.yaml file. So you want to make sure you have these two lines. One is the file path, and then another one is the map start at doc and set to true. And after that, it's pretty simple. All you need to do is rebuild and then run your launch file again. So if we go ahead and run this, you should see that our Rviz will now have the map automatically when we start it up. So I'm going to minimize the Gazebo, and you can see here that our map is already up and ready. Okay, so now you could use this for localization with like the nav toolbox and things like that. In this ROS2 navigation tutorial, I will show you how to use nav2 to navigate to your mobile robot in Rviz. So if you haven't seen this video already, go ahead and check it out, the Slam Toolbox simulation tutorial. We will be building on top of that, so it might be useful for you to check it out. But in this video, our main focus will be the nav2 toolbox. So we will go over how to install the nav2 toolbox, go over how to remap the command velocity for nav2, go over how to start the mobile robot simulation and view the SLAM map, talk about how to start nav2, go over how to set up the cost map in Rviz, and finally go over how to navigate your mobile robot with nav2 in ROS. Okay, so to install nav2, it's pretty simple. You want to run this command here, sudo apt install ROS, and your distro version, I'm using Humble. But here you have two main things. You have the navigation 2 and then the nav2 bring up. So once you run this command, you should be up and ready to go. Okay, so now I want to talk a little bit about remapping. So when you use nav2, by default, everything is set up to work with command velocity. So one of the things to note is that if you have a robot set up, sometimes by default, you might be using a different command velocity. So in our case, in our previous SLAM tutorial video, we were actually using the diff cont command velocity unstamped. So in order for nav2 to work, you actually need to remap it. So I go over step by step how to do that in more detail in one of my documents here, the how to remap command velocity for nav2.md. It's on my website, so you could go ahead and check it out. I'm going to link it in my comments below. But the main idea is you want to go into the launch file and then edit that. So I'll lay out the details there, so go ahead and check it out. So now we're going to talk about how to start our mobile robot simulation and view the SLAM map. So go ahead and cd into your folder, source, and then we want to run this command here, the ROS2 launch wheel robot gazebo.launch.py. So this will start up our Rviz and Gazebo. So I've already sourced it and everything, so I'm just going to run the command to start it. And once you do that, you're going to see your Gazebo show up. So this we covered in our SLAM tutorial on how to set that up. But our main focus will be Rviz here. So Here you can see we could view our simulation in Rviz. We've created our map previously in our SLAM tutorial, so you could try to play around with creating different maps if you don't like how your map looks like. So it's going to be a little bit of trial and error. So here you can see that all of our map has been loaded, and then our next step will be to set up some of the cost map, run our nav2, and then we could actually start navigating it. But this will be the foundation to get everything started. So make sure you can do this properly. So how do you start nav2? So what you want to do is we're going to cd and then source inside another terminal, and then we're going to be running our ROS2 launch, the nav2 bring up navigation launch.py, and we want to use the simulation time to set to true because we're using a simulation, and we want the other stuff to be in sync, the other nodes that we have set up. So if you go ahead and run this, this will start up the navigation, and this will allow us to proceed in our next step later, which will allow us to set up the cost map. But to actually see the cost map, you need to make sure that we run this launch file. So what this does here is it'll tie some of the commands together to our actual robot, which we'll see later on when we're actually trying to navigate it. So right now we see our typical map, but what we're going to go over now is how to see the cost map in Rviz. So to actually see your cost map in Rviz, you want to click the Add button in the panel under your displays here. And there's a couple ways to get there, but usually I like to go to the By Topic tab, and then you're going to see here the global cost map, and then the map. So once you see the map, you want to click OK. So you can see that there's these regions that pop up. So the gray regions are what it expects to be obstacles, and then the white is not obstacles. So you can see it has a general outline of the square that we previously created, which represents the walls. And if you want to change the color scheme, what you can do is come down here and then click on cost map. This will give you a colored view, which is a little bit easier to see. So that's just an optional setting that you can play with. The final step is to navigate your mobile robot using nav2. So now that we have set up everything, we have our map visible, we set up our cost map, and we also launched our nav2 with the nav2 bring up. This will actually be connecting the command velocity to the actual robot. And if you've done your remapping properly, which I've laid out in my website, then your robot should be actually connected. Because otherwise, if the command velocity is not mapped properly, then your robot will not move. So you want to go up here and click on the 2D goal pose. And then once you do that, you could click a starting point, and then you could drag the arrow to where you want it to go. And once you drag it to the direction that you want to go, you release your mouse, and then your robot will start navigating. So what this is actually doing is it's sending pretty much the commands to navigate the robot. So you have like some direction and some angle. And sometimes the robot freaks out, as you can see here. So you could look into details of why that's happening. But you can see as it keeps moving, it eventually kind of steadies a little bit in terms of the direction, and it finally settles to a final direction. So this is a little bit glitchy, probably because the map is not perfect, but you could play around with that and see if generating a new map might help. So hopefully you learned a lot in this ROS2 course. If you want more material on robotics, AI, machine learning, controls, or computer vision, make sure to check out my YouTube channel. I have a bunch of playlists and videos on various topics that I think will be very useful for you. So go ahead and check it out. Make sure to subscribe, and I'll see you later.